Good morning, everyone, or good afternoon, or good night. I don't know where you're located, but anyways, welcome to the first Data Science Summer School organized by Hertie School Data Science Lab and Data and Methodology Center at the Scripps Cluster of Excellence. I would like to thank our funders, the Scripps and the Stifterverband, for their generous support. And I'm super happy to see you all here, both on Zoom and in the parallel stream session on YouTube. And I would like to note some organizational and technical details about the session. If you're in the Zoom meeting, you're all muted and your cameras are off upon entrance. Please do not unmute yourself or turn your camera on unless you have a question. We really ask you to put questions in the chat. That way it's going to be easier to handle them for the TA and the instructor. And if you really want to speak up, if you don't want just to put question in the chat, you can raise your hand, and then whenever there's going to be a good time through the session, we will let you unmute yourself, turn your camera on if you want, and ask your question out loud. If you're on YouTube, you can leave your questions and comments in the live chat, and we will handle them as soon as possible, either by responding them ourselves or directing the questions to the instructor and the assistants. I also want to remind you that this Zoom session is being recorded, and thank you very much in advance for following these rules. And today we'll move to a very interesting topic, deep learning. It is in a way continuation of yesterday's session. And today we have Dr. Christian Arnold as our instructor. And I would like to introduce him a little bit. He is a senior lecturer at the Cardiff University in using data-driven methods from statistics and machine learning. His work lies in the intersection between social science and computer science. Recently, he has been working more and more with neural networks to tackle challenges in data privacy, natural language processes, and applied computer vision. His substantive research focuses on institutions and governance and what drives and determines the rules of political decision-making. Prior to joining Cardiff, he had a position at Oxford University and worked as a data scientist in industry. He's a member of the Academic Advisory Board for the Government Statistical Service at the Office for National Statistics. And his focus there is on all matters related to synthetic data. And Chris, the floor is yours. You can share your screen now, and thanks everyone.
Hey, hello. Thanks, Olga, for the great introduction. Let me share you my screen with you. Okay, here you go. And I hope this is working.
Yes,
otherwise,
perfect.
Marcel,
we can see your screen.
Can you see it? Is it better now?
We can see it very well. Thank you.
Okay, cool, awesome. Yeah, thanks for the great introduction, Olga. Thanks for all support and here in the summer school. This is really helpful, Olga, Carol, and Hertie. Thanks. It's a great pleasure to be here. I have a TA on my side, a good friend and co-author, Marcel Neunhofer, who is a PhD candidate still in Mannheim, but he's moved to LMU Munich, and he will be handling your questions today and forward them to me and help me in all matters. Let's kick it off. Today is about deep learning. Some quick logistics before we start. I made a repo with all the material that you can find on my GitHub page. It's called Civica DL class. Go there. I think we already posted the link to it. You should find the code there. If you open up these notebooks, they are Colab R notebooks, so you can click on the link. It will guide you to an online instance where we can execute R code later. I posted all the slides and math there, but this really is just for later at your own reference. You don't have to take a look at that now. Just follow the presentation slides, and then I will also write up some maths here on my tablet and live screen that to you guys. It's a little bit like a whiteboard, and we can use that. In case there are any questions, so I am in full screen mode here, pretending that, no, I don't see your comments. Marcel will see them, and he will forward any kind of questions that there are at a time that they make sense. So he knows where I'm going and what good time points are to stop me maybe. And apart from that, I'm alone in this room speaking to a screen. And yes, this is a bit odd, but this is how it is in these times. I'd love to be in the same room with everybody and just get this workshop vibe in a classroom setting where you can see each other and yeah, read off your faces whether I make sense in what I'm saying or not, whether it's too complex or too quick or too fast or too easy. I can't do that, unfortunately. So yeah, we are all used to this setting by now. So I think we will make the most of this. We will start in the introduction with a quick motivation. So a little bit about myself. I strongly believe that this is the most exciting time to be a social scientist in like ever. We're living in a time that's totally amazing and really important for everything we want to study about society. The simple reason for that is we have tools that allow us to do that at an unprecedented level. So first, there are a lot of new opportunities. Think about, and I think that's a really important cornerstone here, is all the data that is being collected by all different sorts of devices. Think about the billions of mobile phones that are being used that collect all sorts of data on an individual level all over the planet. Excuse me. This is data that is hanging around somewhere on some servers, and obviously you can't access them for very good reason, but it is data that is out there. A lot of people are using social media and to communicate via social media, so a lot of data is being gathered in that realm as well. Everything we do online, everything is trackable, and even what we do offline is sort of trackable. Think about security cameras that show what we are doing. Think about the different ways in which this data is being used in democratic societies, not so democratic societies. This is an amazing amount of data that is out there. And once data is there, somebody will probably start working with this kind of data. Then we have a massive explosion of computing power. We have now even computer chips that have been optimized for all kinds of powerful machine learning and deep learning models so that we can make the most of them. And both data and this computing power didn't exist even 10 years before, right? And then think back 20 years when the internet was just starting. This is really a crazy time. Now, the other side of it, and that's an old Spider-Man phrase, I think, right? A great power bears great responsibility. I really believe that we are at an important crossroads in social sciences where we have so many more opportunities and where we as analysts, as people who understand both the theory side of social science, but also increasingly the computing side and work together with computer scientists and mathematicians to make all this work. We have a lot of responsibility, and it might be a bit too much pathos maybe, but think back about what physics did when they discovered and how to make use or misuse of atomic fission and the capabilities to build weapons and all sorts of things that have massive impact on how we live on this planet. I think we social scientists have that now too. And we have to be really careful. And there is a big moral component that is definitely worthwhile exploring. And if we had more than 4 hours and a whole day workshop, I'd love to chat with you about that. I have something in the appendix today. So in the end, if we have some time left, we can have a quick chat. It's also, of course, very inviting to talk about these issues. If we had a normal workshop session over a beer or a pint or a coffee in the afternoon, unfortunately, we can't do that either this year, but these are important things. And this fascination goes hand in hand with this responsibility that we have. And I think that's something really important. And that's sort of in the background of what we will be doing today. Olga already introduced me. But a couple of words about my own background. So I am based at Cardiff. I have a PhD from University of Mannheim, from the beautiful grad school there. I use deep learning in a couple of projects. So for example, I use images to detect voting fraud and voting irregularities in a larger project. I work on synthetic data with Marcel, and then privacy concerns. A lot of deep learning is happening there. I also work on text, but there's no deep learning, like interesting deep learning involved in that. Yeah, so this is stuff where I work with this. I also have an industry background. So I worked for a startup, which got then bought up by a large company. I'm in touch with the ONS, the Office for National Statistics. I do some knowledge transfer for the National Democratic Institutes, who running voting observation missions, and we help with the technology stack. So I know a little bit of both worlds, which is, I found it very interesting and really rewarding to also see how the stuff that we develop in academia can be used in practice out there for all different sorts of things, for the greater good of all, of course. Okay, let's have a quick chat about why we actually talk about deep learning. Why is this interesting? So deep learning is a subset of techniques, of tools, of models from machine learning. So machine learning, those of you who were here yesterday might remember that, is basically the idea to optimize a certain cost function on the basis of some evidence that you see, and learn about the parameters in your model, and try to make that work. Deep learning is all about one class of models, and by class of models I really mean that, right? It's not just one model, a neural net. Neural nets can be really like everything you want them to be. And I like to think them as a big Lego box, and this is what I hope the impression you will get today. A big Lego box of all kinds of models that you can stick together in a way that you want, and build something that is useful and help you make sense of the tasks that you're actually doing. One of the key distinctions between a normal machine learning model and deep learning is that you do not necessarily require feature definition. So you don't have to think about what variable goes in there, how do I convert that. No, it's a little bit like you can throw literally anything at a deep learning model, as long as you know how to convert it into data, into a data flow, into any data format. And we will take a look at some of these ideas that you might not be used to today. So we will start right out with a computer vision task, for example, simply to get you social scientists, and I assume that this is your background, away from the idea that data always has to be a nice spreadsheet, right? Data can be all sorts of things. Features can become a byproduct, and there's a bit of a hype about word embeddings in the social sciences at the moment. People do a lot of things with that, and this is one of these byproducts of deep learning, and that comes out of it at the end of the day. Then deep learning outperforms classic machine learning approaches. Not always, right? You really have to be careful, like when do you actually want to use deep learning models? If you are speaking about data sizes that are moderate from a machine learning perspective, say 10,000 to 100,000 observations, then your standard machine learning model might give you the same performance or even do better. But deep learning is particularly powerful if you have vast amounts of data. And by vast amounts of data, I am really thinking like billions of observations. So if you are a big tech company and you run a social media platform, you will have trillions of images. And if you use those trillions of images that even might be annotated in some kind of way, you can then train deep learning models that will become really powerful at the end of the day. And this is where deep learning outperforms classic machine learning approaches. A brief history of neural nets. So neural nets have been around for quite some time, right? They even go back to, I think, the 60s, the idea of a neuron, how we could formulate that. And at the end of the day, this is a logistic regression. And again, this echoes nicely what Marcel did yesterday, and we will pick it up exactly there. Key ideas about how to train deep neural nets have been developed in the 80s already independently by several groups. Something called backpropagation. We will take a look at that later as well. But people found that training was challenging given the compute power that was there by the time, and the way how people thought about how these neural nets were behaving. They fell out of favor from a lot of people. And in the 90s and 2000s, only some people in, I think, maybe Switzerland and Canada were ever concerned about that and kept on doing research on these things. In the mid to late 2000s, there were some breakthroughs in our understanding about how to train them. Something like ReLUs, rectified linear units, regularization, but also hardware made it possible that we could advance here. And we will take a look at these innovations. And they, like now, 15 years later, they're more than surprisingly simple, right? But they helped a great deal. And we will take a look at that later today, of course. And since the early 2010s, when we had a lot of data coming in to train them and a better understanding in how to estimate not only shallow nets, but actually really deep nets, a lot of attention came into that. And with that, a lot of, I don't know, startup money and everything really became crazy. And everybody loves deep learning in these days. And let's see where this is going. A quick look on today's agenda. We are still in the introduction, and I'll keep it at that for a couple of minutes more. We will take a look at how to train deep neural nets for pretty much, everything before the lunch break. So I really want to go with you in depth here and take a look at some maths, because I really think it is useful to understand what is going on behind the scenes so that you get an intuition about why these neural nets behave the way they do. And as you will find out today, they can be quite fickle. Okay, so it's not easy to estimate them, to get them to a level where they run stable, like, I don't know, you type in a stata or an R command, and a couple of seconds later you have a result. You need to be able to control them fairly well. To do that, I'll teach you all I know about tuning, about first how to fit a model, and then how to avoid overfitting. And striking the right balance so that you really have a well-oiled machine that does the job for you. And most of the day will be spent on understanding really well the fundamental aspects of deep learning and how this all works. And in the outlook at the end, like the last half hour or so, we will take a look at all sorts of different architectures that you can now start building from that. Okay, so it's a little bit like a 101 on how to use Lego bricks, and then I'll show you all the kind of fancy houses, cars, and spaceships that you can build later. How does learning work today? So I like to think when it comes to learning about knowledge, experience, and skills. So knowledge is the stuff that, like hard knowledge, that goes from my brain into yours. I hope in some kind of spoken language you can deepen that by reading up in books, in the sources that I have in the appendix. Experience is really experiencing how these deep learning models work here in this context, get an intuition about what to expect, what does work, what does not work, and so on. And when it comes to skill, this means like practically doing something. I cannot teach it by showing you. You have to try this out yourself. So this is everything related to programming on your own. In the first section, what is deep learning? I'm talking a lot about what it is. So the focus, you can see the large X here, is on knowledge. I will throw you into some code right away in a couple of minutes, though. Then we will understand how do deep neural nets learn. After the lunch break, I want to cover how deep neural nets behave. So get some experience with that, running some code, using a playground. Excuse me. We will then learn how to write code for deep neural nets. You can see, against a little bit of experience gathering, but a lot of skill development. And finally, I want to wrap it up with typical architectures and practice. Okay, before I jump into the first model, any questions so far? Marcel, is there anything that came up?
Oh, so far you can keep going.
Okay, then I'll keep going. Then allow me a sip of water, please. So before I start explaining how all this works, I want you guys or you folks to run your first model. And we will use one of the most classic data sets there are in computer science. It's called the MNIST data set. And it is basically 10,000s of digits that had been handwritten on envelopes in the 80s. And somebody scanned them back in those days. And now we have a beautiful training set that we can use for all sorts of things. And this has been a classic challenge for all kinds of machine learning models in the 80s, 90s, and early 2000s. Today, it's sort of solved this problem. And I can show you how easy it is to actually solve this problem. Okay, so what you can see here are overall 70,000 digits that are all represented in pixel boxes. Okay, so each of these squares are a 28 by 28 pixel box. So this is basically what you would think of as a spreadsheet in a social science context. And the color that you can see here is represented on a scale from 1 to 255. Okay, so it's the lighter or the darker it is, the more it gets represented or less it gets represented by a number. And so overall, we have a stack of 70,000 spreadsheets that we can stack on top of each other. And we will process that now. And what we want to find out is we want to train a model that reads in that data and that learns what kind of digit is behind that. And the goal is to get more data in without a label and predict the label on them. So if we see such a picture, for example, is this a 0, is it a 9? We want the computer to recognize that. The same for all the other digits. That's the task. And for that, we will have our first playtime here, and it's code number 1. The goal is to get a first impression of the performance of neural nets. So how powerful are they? And also a first impression of the code that we will use. Let's open up the workbook, and we can see what we make of it. So this is my repository that I put together for the class. These are the lecture slides, this is the maths, and here you can see the notebooks. And if you click on them, you can see this tab open in Colab, and it will lead you right to something like this. Okay, so all the code is in there, and we can start working with it from here. This is a bit weird. Okay. Okay, for the code, like we are using R as our computing language, and in R we will use R basically as an API to use a language that helps us write neural networks in a really efficient way. And this library is called Keras. There are currently 2 main libraries that help us formulate neural networks in a really, really easy way. Keras is linked up with Google, I think, by now. And there is another one called Torch, who is owned or run by Facebook, I think. And both of them are really useful. Keras might be a bit more popular in the business context. Torch a bit more popular in the scientific community. If you were in Marcel's class here yesterday, there is apparently already an MLR3 Keras option there. So you can even run Keras from MLR3 in the MLR3 context. And we will use Keras in R right away. You can access Torch and Keras, by the way, of course, also from Python in case you prefer that. That's totally valid. Okay, so we first install our package Keras and then call the library, and that takes you about a minute. Then once we have that, we will download the dataset, and the dataset MNIST is somewhere in part of the Keras package, and this should be pretty straightforward to download that. You can investigate that dataset a little bit, and we want to do that. We want to extract first the train images, and if we do that, we can see that the train images are a stack of 60,000 spreadsheets, and each spreadsheet is 28 by 28, right? So it's a rectangle, and we are building up this big tower here. We want to reshape that so that everything is in one big spreadsheet. So what we do is, instead of having this stack of spreadsheets, we want to have one large spreadsheet, and we will flatten out this 28 by 28 matrix into a 784 line, so to speak. Okay, so we take each row, stack them up next to each other, and have one big massive spreadsheet here. That's the kind of data that we want to do. Then, as I told you, everything in these images is coded as a scale between 0 and 255. And neural nets really hate any kind of value that is beyond 0 or 1, beyond that absolute range. Why? We will get to that later. It has to do with something called vanishing gradients. You will understand that in a couple of hours. The important message is here we want to divide by 255 so that everything is between 0 and 1. Then we do the same thing with the test data as well. Again, we get an object that is 10,000 long and 784. Again, why 784? Because it's unconstructing this 28 by 28 matrix of each of the images. Then we have our targets, which are the labels. So the first image would be a 5, the second image is 0, the third a 4, and we want to expand that to a matrix of variables, right? So we basically build dummy variables from these targets. In computer science lingo, this is a one-hot encoded way of annotating it, and it basically says, well, you have one row here for the zeros, one for the ones, one for the twos, one for the threes, and so on. And if it is not if it is not a 0, for example, then it is a 0. Sorry, let me make this a 5. If something is not a 5, then you have encoded it as 0, and if it is a 5, then you have encoded it as a 1. And this is simply a way of storing the data. Okay, let's run the model. This is how you define the network architecture. I'll walk you through why that is and how that works in a second. So we first have to build the model, and this is what we did here. Okay, so we have a network, and we can call that object. This is how it looks like. We'll take a look at that later today. We then compile everything so that the computer can actually read it with a couple of hyperparameters. We'll take a look at them later. And then we simply run everything, and we have the model run for 5 epochs here, so 5 iterations. I'll walk you through how that is and why that is later today. This is really just to show you how easy it is to actually run all these things. Running the model should take a couple of seconds. Not very long, though, for this problem. And we should be done any minute. And once we are done, so we save all this training effort in an object, and that's called history. Once the training is done, we can actually plot history. And before that happens, I'll have another sip of water. Okay. So here you can see something that's called loss. We will cover that later. And here's the accuracy of our prediction. And you can see it starts in the first epoch at something like 90% already. And then after 5 iterations, we are at, somewhere close to 99% of accuracy. So in 99 out of 100 cases, with a fairly simple deep learning model, we are getting to something that yields us impressive results, given what we believe complexity of the prediction tasks that we have here. Okay, this is really just to show you how easy it is to write that code, and we will follow the same recipe always. Okay, so we in all of the lab sheets and in everything you do actually in deep learning, you first have to prepare the data and get it into a format that's easy to read for the machines. Then we write the model, we compile the model, and finally we train the model and want to tune it and what have you. But it's always the same recipe that we'll be following on the code side. Okay, this is where we are. Let's walk you through some deep learning in a nutshell, unless there are any questions at this stage. But I don't know, Marcel?
Not yet.
Cool.
I think
okay.
they're coming soon.
Feel encouraged. There are no stupid questions. If you don't understand something, you might not be the only one. So please don't hold back. Okay, so how does this deep learning actually work? Okay, why do we talk about deep learning actually? Like, what is deep here? As Marcel mentioned yesterday already, it doesn't have anything to do with the depth in your understanding. It has something to do with the depth of the model that you're actually constructing. Okay, so it was a term coined to differentiate like shallow or normal neural networks from deeper neural networks that you can stack. Okay, so what we have, or what we can easily do here in deep learning, is we can stack layers of neurons, and we pass our information through that. Here, an original input of the MNIST data set. Okay, this is this 28 by 28 matrix, and we have a final output. Okay, remember this is basically these are 10 variables that we have, and we want to identify or we want to predict the one variable where we observe a 1, and we want to predict zeros for all other categories, right? This is the tasks that we are currently looking at. So what is actually happening at each stage? And this is really very rough, very high level understanding of what is going on. So once we input data here, we will have layer 1 representations, which might still look like this. And the higher up we go, the more coarse they can become sometimes. In particular, if we narrow the amounts of neurons that we have, the closer we get to the output. So the output in the end, in higher levels, might not always look like something that we as humans can interpret here. And this holds for this kind of deep neural network that we are constructing today. When we talk about computer vision and something called convolutional neural nets, this might be a little bit different, but for now, it's sufficient to say that this information that is being piped through in the kind of easy deep neural network that we are estimating can be chopped up in this kind of way. How do we actually train neural nets? And this is the mantra, and that we will always follow it. Okay, so the first step that you do with a deep learning model is you predict an outcome, and you throw data into a computer or into the neural net. It predicts an outcome. It then checks against the real data that it has, okay, and sees how wrong is my prediction from this real data. It propagates this information back, and then it updates the weights of the model. Okay, so it's always a passage of information to the prediction, see how wrong the prediction is, and a backflow of this information. We call this forward propagation and backward propagation. Once the weights have been updated, we run the same thing again. Okay, back and forth, back and forth. And this is the mantra that we will be following you will do that for every single neural net that you're actually training. And to properly learn how to do that, let's go and take a look at logistic regression, simply because logistic regression is sort of where everything started when we started thinking about neural nets. And as you will see, you could probably think of deep neural networks as some sort of hyper-connected, multi-level logistic regression from a statistical point of view. It doesn't really make sense though, right? But it's sort of a gut intuition if you come from an econometric training. How do we estimate or how do we train this logistic regression with something called gradient descent? We will use our 4 steps. We first predict a result. We calculate how wrong the prediction is, and then we propagate the information back and update our weights, and everything starts again. To do that, I will use my whiteboard, and I'll write down everything I have here on my tablet and share that with you in a second. You don't have to pin that down on your own. I uploaded the PDF with all solutions already to the repository on purpose, so that you can really sit down and follow me while I'm writing down that. We will first do a refresh in logistic regression. We will then try to understand what gradient descent is, how that looks like. And it's sort of again, sorry for making that reference again, in case you were here yesterday, Marcel walked you through how to do gradient descent with code. I will do the same and run you through that, how to do that with maths. And we will then take a look at how to do logistic regression via backpropagation of errors. And once we have that, I think you will have earned your first break.
Before you switch to the whiteboard, there's some great questions in the chat.
Yeah,
so 2 of them, Tanmoy and Asimaba, I hope I pronounced those names correctly. Please correct me if not. Have questions about the number of layers. So the first is, and maybe Tanmoy, you need to clarify what you mean by that. Is by any chance, is prediction related to the number of layers? And the second question regarding number of layers is, how is the number actually decided? And does that depend on the model? And then we have a more technical question by Daniel. I will refer to after the whiteboard session, I guess.
Okay, cool. So the number of layers, I hope in 2 or 3 hours you will understand much better how this all works out, but let me give you a brief answer already. So the number of layers and the amounts of neurons that they put in there basically tell you how powerful your net is, and how well it can abstract the information and turn it into something that it can use to make the prediction. And that's a very high level answer, I know, and pretty vague, but that's actually what is sort of going on there. The exact number of layers that you want to choose, that's a hyperparameter that you will be able to tune. We will talk about what hyperparameters are and how to tune them after the lunch break. But this is an important question. Something that turns out to be really working well are exponents of 2, right? So in neural network architectures, you will often find the numbers, I don't know, 16, 32, 64, 128, 256, 512. And also the data that is being piped in will follow these chunks often. And the reason is that it's really easy for a neural net to scale the information up or down. Apart from that, neural networks have, like, we still don't know enough about the theories about why and how neural networks work. And the computer science literature around that topic is often driven by, hey, this works, and then let's try to figure out why it works. So don't approach that from an econometrics point of view, where you have a statistical theory that will guide you in, and I don't know, your knowledge about distributions, and then how you can set up an estimation thing, and then everything, and that you can be sure about the statistical properties of the model that you're running. This is not how neural nets have been developed and how this literature is sort of working. It's much more experience-based than anything else. Okay, does that help? Let me go and see the chat.
Yeah, both seem happy with your answer. So.
Okay, beautiful. Then let's take the more technical one later, if Marcel says that this makes sense. Okay, let me stop sharing for a second, and I'm going to share now. My whiteboard. So can you see that? Marcel, this is okay?
Yes, perfect.
Okay, cool, beautiful. So excuse my handwriting. This is my handwriting. I apologize. I got bad marks at school, always for that. I'm doing my best to really write everything up in a way that makes sense for you and that is nice and readable. If you can't read anything, I apologize, and please do ask. But yeah, I'm really doing my best here in trying to have something nice. As said, all of the maths is already fully uploaded on the repository, but I think it makes sense to for you guys to watch me walk you through some of the equations. And I like to do that in this kind of whiteboard fashion because it's easier to process, I found, at least often when I was a student. So I think it is a great exercise. So we will first take a look at logistic regression, and you will get the greater picture while we do that and why we do that. And while I'm doing that, I will use something that you all are maybe familiar with, which is a logistic regression. And I will continuously introduce the computer science annotation of it and the computer science lingo. And it's the same logistic regression, but computer scientists sometimes, since they discovered it themselves, of course, they sometimes have different annotations. So remember that in a logistic regression, what we want to do is we want to come up with an estimate of our y. Okay, so that's the goal of everything that we do. And this y is the probability that y equals 1 given our data. In computer science, we have parameters. We call the parameters W, and their element R and X. And we have the biases. So W is weights and B is biases. And the biases are our element of this R. It is nothing different than this bias is your intercept in econometrics, okay? And these weights are your regression coefficients, okay? But we will refer to that in a way that we use, that they are being used in the deep learning literature. So no more regression coefficients. We will only talk about weights and biases from now onwards. The function that we want to estimate in logistic regression is sigma W transpose X plus B. Okay, and this is, you are now back in safe territory, right? This is a linear component, how we know it from econometrics, only with different letters. This is what I told you. And in a logistic regression, we know that this sigma is a function of z, and it is 1 over 1 minus e to the power of minus z. Okay, pretty straightforward. We all know that. We know how this goes. Now, the first thing we want to define, is something that is called a loss function. And the loss function gives us information about how far we are off, how far off is our prediction from the real results. And all this training, all this optimization is done to minimize this loss. So the smaller the loss is, the better the neural net is at predicting. And this loss depends on y hat and y, and it is typically written as follows. So it is y times log y hat plus those instances where y equals 0 times log 1 minus y hat. Okay, that's pretty straightforward. So let's first take a look at what happens if y equals 1. So if this guy and this guy, like the real data actually is a 1, then this this loss function that depends on y hat and y will simply boil down to minus log y hat. Okay, and it's easy to understand because if y equals 1, then this becomes a 0. You can forget all about that. Y equals 1, and we take the minus sign here and end up with minus log y hat. Let's do the same for the case where y equals 0. And here, our loss function y hat y is simply minus log 1 minus y hat. Okay, again, the same logic. Y is 0, so this term vanishes. This becomes a 1, and we are left with this term, and we get the minus from all the way here. So this guy will become, in our training, this can be, we want to have it as large as possible, but not greater than 1. And this as small as possible and not smaller than 0. That's the goal of this, of the cost of the loss function. Now, in computer science, we can also find a reference to the cost function in contrast to the loss function. And the loss function here, this guy, is the general expression of what is going on. If you actually pipe the data through and actually calculate that, then computer scientists speak of the cost function. Okay, the cost function J, this is really important, is not just the function itself, it's actually the function in the context of data. So you sum up with a sigma for all of the cases I until m, the loss function that you have, and then you divide it by m, and that's your cost function that you actually want to minimize in your algorithm. And if you write that out, you can see that I only added here this sigma minus 1 over m. We now have these indices here, and that's simply how that goes. Pretty straightforward. Okay, we've covered loss function and cost function, and that's something really important that we need to understand in order to do something that is called gradient descent. And in gradient descent, what we are doing is we want to minimize this cost function. Okay, so we want to minimize the difference between our prediction and the real data. And the way we do that is as follows. So this is the cost, and this is here our parameter space for the W's, just as an example. And how our cost function looks like is something like this. Okay, it might be much more complex and in many, many different dimensions, but it's basically a mountain area with valleys. And the goal of everything we do is we want to understand, like, where's the minimum? What's the beautiful spot here where we can get to the bottom of this valley? Okay. So we start by we start with an arbitrary value for W. Okay, this is our W for the W0, the one that we typically have. And the way we update this W is in the following way. We repeat the following equation. We take the W from the previous round, the weight from the previous round, and we add or subtract the derivative of the cost function that here, for that sake, only will depend on our weights towards the W. So this guy here is the derivative of the cost function towards the weight. And this guy here, alpha, is a really important hyperparameter, that is the learning rate. So let's see how this updating of our weights will actually work in practice. Okay, so in the first round, we have a value for W. And this is our W0, the randomly chosen starting value of our weight. And we estimate, or predict, more to say, we predict a result with our neural net. We calculate the difference between the real outcome and our prediction. And we then use that information in order to update the weights that we have been using. Okay, so imagine that there is a big, big difference between our randomly chosen starting neural net with this weight W and what we've been seeing. Okay, so if there is a big difference in that, then the derivative of the cost function towards weights, like the change of the weights, the change of the cost function by changing the weights by 1 unit, is fairly large. Okay, so we know that we will update like this. You know that this part is a fairly large value. So we will subtract a fairly large amount of that from our existing weight and update our weight accordingly. So we move W0 into that direction, and we will come up with a new value, W1, that is more into that direction. Okay, so quite a big jump. Now, we predict the result again in the forward pass in the second iteration. And again, we get a difference, and this difference between the real world and our prediction is smaller now. So the derivative of the cost function towards dW by a change, by an infinitesimal change in W, will get smaller, and our updating of the W will be a bit less so in the second round. Okay, so we might only update until here now, and this is where we end up in the second iteration, and this is how it all continues until we move it further down. Okay, so W1 becomes W0 minus the learning rate and the derivative of J towards W. And this gives us our W1, and in the second iteration, we use W1, calculate W2, and we subtract from it the derivative of the cost function towards dW. Okay. And let me move that a bit down here. And then we would go on. With a second, with a third one, with a fourth one, with fifth one, and so on. The role of the learning rate is, of course, really crucial here. Okay, because the learning rate will tell us how much we actually update this guy. So if we have a really small learning rate, and let's use this gray color to do that. If we use a small learning rate, even though the derivative might be fairly large, we would only use fairly small steps to go down that line. Okay, and approach this minimum in much smaller steps here. What happens if we have a too large learning rate here? Well, if we have a learning rate that is massive, and let's use the pink color here. If we have a learning that is massive, we would jump from this W0 here with a massive jump, for example, all the way here. Okay, and then this sign would flip, and in the next round we would probably jump somewhere here again, and we would jump back and back and back, and we don't, like, learning would take a lot of time as well. So the learning rate is a hyperparameter that we will have to optimize. We have some good guesses about roughly how large they should be, but the exact value of it really depends on the problem you have and the kind of data that you want to predict here. Okay, let me write up the general case for you, so that we have this nice and complete. Because this result is really an important result, and we will see that on a lot of occasions today. Our cost function depended on the weights, which are our former regression coefficients, and our biases, our former intercepts. Now, the way we update our weights is the previous weight minus alpha times the derivative of the cost function that depends on the weights and the biases in a real setting towards W. And the biases very similarly are calculated as the biases minus the learning rate and that's the cost function that depends on W and B towards dB. Okay, and this is how backprop works. And this is sort of the mathy side of things that Marcel showed you yesterday with code. And I hope it gives you a really good intuition about how this optimization works. And it's basically, and this is the last picture that I will use here, it's basically like having a ball that is rolling down your hill. And keep that image in mind, because we will use that image. We will use that image later on when I explain more about variations and modifications about optimizers. But that's something that we might find very useful when we think about that. Okay, so whenever there is a ball that runs down a steep hole, it will be very fast. Okay, so it makes a lot of movement in 1 second into that direction, and the flatter it gets, the slower is the ball that is rolling around, and it might even do these movements down here until it really finally rests at the valley of everything. Okay. Let's take a look at how this idea of gradient descent actually helps us with the logistic regression backpropagation. So the goal that we want to do is we want to update the values of our logistic regression. Remember that we start with w times x plus b, which will give us a certain value that's called z here. We will use that z in the sigmoid function that we write like this. And the outcome of it is called A. And this is me again introducing a little bit of neural net lingo. E is called the activation. That's the outcome of your neuron. And why is it called activation? Because you will see that these, like the output of one neural net can often become, of one neuron, sorry, will often become the input of the next neuron in our neural net. We will refer to our outcomes as A, activation, and it is basically the y hat that we're all used to. And then for the logistic regression, if we use A instead of y hat, we have minus y times log A plus 1 minus y times log 1 minus A. It's the same thing as before, we only replaced the y hats with the a's here. So to really make this nice and visual, let's think of a case where we have two variables. Oh. So we have x1 as data and accordingly our weight 1. We have x2 as data and accordingly our weight 2, and we have b our bias. And we will now feed them in to our equation. Z equals w1 x1 plus w2 x2 plus b. We use this to calculate our y hat, which is the activation. And that's the sigmoid of z. And we can use that activation of the y hat to calculate our loss function that depends on y the real data and a the activation, our prediction, so to speak. That's our refresher, and we talked about that already. Now, remember that in order to do our backward propagation, we want to end up somewhere here. Okay, so we want to know the derivation of the cost function towards our weights and towards our biases. And this is what we will have to calculate. And I will simply throw the results at you. So, and you can try that at home if you want to really work that out from the cost function properly. So the derivation of the cost function towards A at here, this very final end, reads like this. It's minus y over A minus 1 minus y and 1 minus A. Now we want to go on and further derive that. And as you notice, there will be a lot of chain derivations going on because we have to derive that thing first in order to arrive at the derivation of z, because here we have the sigmoid function. Okay, so we first want to derive dA, which is this guy, towards dz, and we'll find out that it is A times 1 minus a. And if we derive everything now together, we end up this and this. We end up with the following, with the chain rule. That's minus y over a minus 1 minus y over 1 minus a times a one minus a. And if you do the math, you end up at a minus 1. There we go. Now, the rest of the derivation is much more simple because we are now, we piped our derivation through this dreadful area of the sigmoid function, and this, to derive this guy is much more straightforward. The result is simply x1 times dz, and dz is this guy here, okay? So this derivation, and dw accordingly is x2 times dz, and the biases are even more simple, as you can easily see, and because they simply collapse to dz here. Now we update everything in just the way we are used to. So W1 becomes W1 minus alpha dW1, right? And by dW1, I mean this guy here. And in a similar way, dW2 is dW2 minus alpha times dW2. And just the same for the biases. Okay, really straightforward. Minus and minus dB. Okay, this where we at with the updating. So what did we do? Well, we learned how to calculate the regression, the logistic regression that we all know already, and it's simply using this function, writing up a cost function that works together with it. Here we learned how to do the forward pass. Okay, so we pipe in data into this first linear component to get a z. We then pipe it through the sigmoid, and this sigmoid will give us a prediction, and this prediction will help us calculate the cost function. And this is the difference between our predicted results and the real data out there. Then we want to calculate the impact of this difference for each of the parameters that we're interested in. What are the parameters that we're interested in our logistic regression? Well, it's the weights, obviously, and the biases, right? The coefficients and the intercepts, if you speak in econometrics lingo. Why are we interested in the derivation of the cost function for each of these parameters? Simply because it will help us at the end of the day to update our values here in this backpropagation algorithm. Okay, so remember that in backpropagation, the value of W1 in the next iteration is the previous value minus a learning rate times the derived cost function towards dW1, and so on. Okay, this is how it goes. And I think I stop here and check with Marcel whether there are any massive questions at this stage.
Nope, everything seems to be fine.
You had a technical question, but
yeah, it's more about computation. Like, I guess it makes sense to address it when we get back into a workbook.
Okay, yeah. So any questions? Any question about computation is buy a good computer. No, sorry, just so I think we are pretty spot on with our break. And if there are no further questions at this moment, Let's have a 5 minutes break and come back at 10:15 if that is okay for everybody. Yeah, cool. Olga, turn off the music. I think it's me again. That's what you wanted to tell me, I guess. Okay, so yeah, let's keep it up. Let's continue here. And now that what did we do in the first hour? We first had a quick general outlook of how the class will run today. We then took a look at logistic regression, at how backpropagation actually works, how we can update parameters of logistic regression, and then we learned how to implement backpropagation for logistic regression, how the forward pass works, how the backward pass works using the cost function, and how we can do that for logistic regression. Now, this is stuff that we know already. Chris, show us something for the deep learning, and this is what we're going to do now. Okay, so we will take this logistic regression and this knowledge about how to estimate them or update them, and put them together to a neural net. And let me share you my screen for that. Here we go. Training deep neural networks, and we will start with something that's called a shallow neural net, and it is called shallow neural net because it simply is not very deep. This is how the logistic regression looked like. So we had a data x1, x2, or even x3, or whatever you might have, and we piped them into a neuron, and we got an activation that is coming out, or a y-hat. How does one neuron look like from the inside? Well, first we use these x1, x2, and x3 to calculate a linear component. The weights depend on the data, and then we also have a bias, and that will give us a z. And then we use this z, pipe it through a sigmoid function, and this will give us an activation, and it will tell us whether we activated or how much activation we can get as an output from the neuron. And this is our usually known y-hat that we already know. Okay, this is how one neuron looks like. And as you can see, one neuron, and this is how it historically developed, was actually built using this explicit logistic regression setup. Now, a neural net simply makes use of that setup and stacks them next to each other, and also, as we will see in a second, in a deeper way. So we have 3 different layers, which means we will need to have a little bit of more annotation. We have a first layer, and I will have superscript and brackets to annotate the layers here. And each of the neurons here, 1, 2, 3, 4 in our example, will be one of these neurons. Okay, so each of these neurons will be a logistic regression. So we enter the data x1, x2, x3 into first this neuron up here, and calculate an activation from that. We do the same thing for the second neuron, for the third neuron, and for the fourth neuron. And we get predictions for each of these neurons. And these predictions will be called activations. So we can see to which extent these neurons are actually firing up. And these activations will become the input of this final neuron. And this final neuron will then decide, in our case, whether we see a 1 or a 0. So this would be a binary classification problem neuron, if you want. We have 3 different layers. This is the input layer. We only have 1 hidden layer. This can be many more. And we have 1 output layer. How do we train this neural net? As always, we just follow our mantra. We will have 4 steps to repeat. We will use it to predict. First, in a forward pass, just like we did with the logistic regression. We will calculate how wrong the prediction is. We will then propagate the information back through the network. We will update all our weights accordingly, right? So all W's in here and B's, all W's and B's here, all W's, B's here, and here, and here. And then we go to the second pass and do the same thing and keep updating our W's and B's. Let's get back to the whiteboard and see how everything we've done for the logistic regression actually pans out when we do that for when we do that for this shallow neural net that I was drawing for you. So I stop sharing here and share my tablet. There you go. I think you're seeing it. If not, Marcel will tell me in a second. Let's introduce a little bit of more annotation, because, as I said, we now have more parameters that we need to take care of, since we have more layers, and this requires a little bit of different annotation. So let's start with the activation function. We have something called like a zero layer, and that is simply our x, okay? And we will denote superscript bracket, that will become our layer.
That's a great question, Chris.
Yeah.
Before you dive in.
Yeah, of course.
Bruce asks, can you think of the neurons as trees and the network as a forest, linking to machine learning yesterday?
So the data goes in so that we don't split up the data here, and I think that's an important thing. We actually run everything through the net. There is a parallel here in a sort of sense, because as we will see, let me see. Yeah, so some of the neurons will adapt to the data in a way that they will actually not let data through, right? So you have sort of an on and off mechanism here as well, that sort of is a parallel. But at the end of the day, it is a different model, right? It's not simply a tree or a forest. It is a neural net, I think. I hope that helps. Okay, let's crack on and take a look at our activation in the first layer. And remember that the activations are the outcome of our 4 neurons that we have. So superscript 1 means that it is the first layer, and A1 is the first neuron, A2 is the second neuron, A3 is the fourth neuron, and A4 is the fourth neuron. So 3 is the third, 4 is the fourth. Okay, this is how it looks like. It's a vector, basically. And our activation here in the second one is the y hat. So this is basically a scalar. Now we have weights. The weights in the first layer, and this will help us think about how this already looks like. Okay, so the weights in the first layer look like this. It's basically a regression with 3 weights. Okay, so we have these are the weights for the first neuron, these are the weights for the second, these are the 3 weights for the third, and these are the 3 weights for the fourth. This is how that looks like. And the weights in the second level neuron, that's the output neuron. Well, we have these 4 inputs, that these activations from the first layer that will come in as, like, the outputs of the first layer will come as inputs to the second layer. So the second layer will be a vector that looks like this. And finally, we have a bias, and the bias is similar to W1, but obviously much shorter, since there's only 1 for each of them. And finally, we will have a bias In the second layer, that looks like this. Okay, so this is simply annotation so that you folks know what we are talking about here and how this is all happening. Let's go and take a look at forward propagation, and remember that we have that this is how the network looks like. We have an output neuron. We have 1, 2, 3, 4 deep or hidden neurons, and we have the data that is coming in. So this is a zoom now that we will do on this one particular model, okay? So for the matter of explaining it on these connections, we'll just forget about them. And I just want to take a look at the first layer and the first model that and the first neuron that we have here. So Z1 in the first layer is the weight, the weights in the first layer of the first neuron transpose times our data plus B1 1, and we end up here with an activation that is the result of a sigmoid function in which we entered this Z11. Okay, makes sense? This is what we saw before. I only introduced a little bit of more annotations by adding the superscript here. And we would do, of course, everything for the other parameters here in the second neuron of this model. So if you think of that in green as the second one, and I can change that into green as well, right, so that you can see that it corresponds to it. It's just the same. And we would do everything for the other 3 neurons as well. This is how everything goes here now. So what do we actually end up with? And as you can see, that deep learning will become will end up having fairly large, they call it tensors, and tensor is nothing different than a multidimensional representation of data. More than, so a spreadsheet is a 2D tensor, a cube is a 3D tensor, and it can blow up fairly quickly, or it will blow up in deep learning fairly quickly. But let's write that down to sort of remain in a little bit of control over it and try to get an overview. So what are we inputting overall in the first layer? Well, here we have our weights in the first layer, and we have our weights for the second model in our first layer transpose. The weights 3 in our hidden layer transpose. This is how that looks like. We multiply that with the data that we have, and then we add the biases. So we have the bias from the second neuron in the first layer. Pretty straightforward, right? So this is the first neuron. We will multiply it with the data. These are the weights from the first neuron multiplied with the data. And here we have the biases from the first neuron, and the same for the second, for the third, for the fourth here with their biases accordingly. And it will give us, in the end, a Z vector, Z2, Z3, Z4, Okay, and I don't want to keep writing that all the time. Oh, let's try to speed this up a little bit. Okay. We will summarize everything here, all these guys with a large W. 1, so it means all the weights from all the neurons in the first layer, and we will use a large Z here. And for that matter, we could, if we want to use that, introduce a B here for the first one. Okay, simply to abbreviate some of the writing effort that I have to do. So we get the activations from the first layer, and that's a nice vector here, and that's basically A1 all the way down to A4. You know the drill by now, and that's a sigmoid of Z superscript 1 that we have here. Okay. Now we abbreviated that, and remember that we want to, something really useful and that keeps you sane when you write up neural networks is to do a little bit of a dimension check, and this is why I want to run you through that, because I think it's very educational in how that looks like. Okay, so again, what do we write up? We have all the Z's from the first layer, and they are basically all the weights from all 4 neurons as input. We get A0. Remember that A0 is nothing else than a different word for the different letter for the data. This is our B here. These are all the biases from the first layer. This is how we can calculate everything. We then have the activations, which are sigmoids of our Z1 from above. And now we go to the second layer, and in the second layer, we proceed in just the same way. Okay, so we have a W2, A1 as input. Okay, so here we piped in the A0, of course. Now we use this A1, these activations from the first layer as input to the second layer. And we add the biases from the second layer. And finally calculate our final prediction. That's A2, which is a sigmoid of Z2 here. So if you read this, this really looks like in the logistic regression setup, right? And this is why I'm making this simplification, because I want to show you that it is, there's a testing center out there, and each morning at around 10:30, they make some noise. Sorry, I hope you can hear me still. If not, Marcel, please tell me. I'll switch to a headset, but I think it's okay. Okay, where were we? Yeah, I wanted to show you guys that this really looks like a logistic regression once you hide sort of the complexities a little bit in there of the neurons, and you can handle it in a very similar way than you would handle it before. Let's do a sanity check and think through the dimensions that we would end up with. Okay, so we know that here the W is a matrix with 4 models, and since we have 3 weights in each of the models, there are 3 columns. Our data that comes in is a 3 by 1 matrix, our biases is 4 by 1, okay, because we have 4 models and we have 1 bias for each of the models. The result of that in terms of dimensionality is that this in matrix multiplication boils down, and we can do a 4 by 1 vector, and we can add those vectors. So overall, we end up with a Z object that is 4 by 1. We use this 4 by 1 object and we pipe that through the sigmoid. It remains obviously 4 by 1. Okay, cool. This is our first layer. So we get an output that is 4 by 1, and this is the input for our second layer, and that makes a lot of sense, right? Remember the network structure here? This is how the net looks like. If we get the outputs from each of these neurons, we will have 4 outputs that are now the input of the second layer here. This is our second layer. Okay. Let's get back to our dimension check. So we get a 4 by 1 input here in the second layer. We know that the weights accordingly will be a 1 by 4 input. Will be 1 by 4, and the bias is 1 by 1 because it's basically one logistic regression with 1 bias, and everything boils down nicely to a 1 by 1 Z. We take that 1 by 1 Z, pipe it through the sigmoid, and end up with a 1 by 1 activation function. Okay, and this kind of exercise can be very useful, A, to understand what's going on, and B, also if you develop at one stage your own neural networks and you really want to write up stuff on your own, it's a good idea to keep track of the dimensionalities. So I think this is really useful and really cool. So where are we in our mantra? Remember that our mantra has 4 steps. Let's check time-wise very briefly where we are, but I think everything looks fine. Yeah. So so in our mantra we had 4 steps, and in the first step we want to do a forward propagation of the information, and this is what we did. Okay, so we used our data that we have x1, x2, x3, and are piping it here through the first layer to get results in the first layer, and this is this bit. Okay, so we use the data, pipe it through, get a Z, we take the Z, pipe it through the sigmoid, and get an activation in the first layer. That's the outcome of the first layer. Now we take that outcome and calculate a result for the second layer. So we take this data, multiply it with the weights, and add the biases, get to Z, pipe it through the sigmoid, and finally get our prediction result, A2. So we are at the second step of our mantra, and we want to know how wrong are we actually in our estimations. And well, what do? We again take the cost function. And this is how the cost function looks like now for our neural network. The cost function now depends obviously on the weights in the first layer and the biases in the first layer. It also depends on the weights in the second layer and the biases in the second layer. My pen is playing tricks on me. And then we write down the cost function in just the same way as before. Okay, this is our cost function. Now, the important bit to understand it, hey Chris, why can't we use the same cost function as for the logistic regression? The cost function depends on the problem that you are having in your last neuron. Okay, so remember that we said, for the sake of an exercise, that we have a neural network that uses this last neuron here to do a classification exercise between a 0 and a 1. And once we know that this is the main task of our neural network, we have to take, or we really should take, a function at the end that does the trick for us. The sigmoid is a really good thing to do if you want to do binary classification. So this is what drives our cost function. If you have a regression problem here, and we will take a look at that later, maybe this cost function isn't your best choice, and you want to have a different cost function in there. If you have multiple categories, like the one we had in the MNIST example, you can use different cost functions for that. So whenever you write down your own model, you should think about what your problem is here. But here is where your econometrics training or statistical training helps you. You've heard of all kinds of models that can actually be used to tackle certain typical data problems that you have, and you can use them and simply use the appropriate cost function here. But remember that the choice of your cost function really is driven by what the final neuron or the final neurons want to do here. Okay, here at this stage, I would go, or if we had a little more time, I would go with you through the derivations of the cost function at each of the stages. Okay, the Z2, and then the weights 2, and the bias in 2. And then once we have that, we would use the chain rule to get to derivatives of Z1 in the hidden layer, the weights in the hidden layer, and the biases in the hidden layer. I think I left them in the notes, so if you want to take a look at them, you can do that in the manuscript. It's not that important. The only thing I really want to point out is that, again, you will find that if you simplify it enough, the derivatives of the weights and the biases in the second and the first layer look remarkably similar. And this is because everything is symmetric here. Everything really looks the same, and you can see that when you derive these the cost functions in a good way. Okay, so we backpropagated the error, and now we have results for the derivations of the weights and the biases in each of the layers. And we finally update our parameters just the way we would do already before. So we have weights and biases in all these layers, and we take the weights or biases from the previous round. We have the same learning rate for everybody, and we subtract weights and biases and update our values. And this is one forward pass and one backward pass. We would now start with the new values for weights and biases. We would start again and do the same exercise again. Okay. So what did we do? We first took a look at how logistic regression works with backpropagation to get an intuition about what's going on, and how we would do that in a very simple setup for one single neuron or for a logistic regression. Now, we stacked a number of these logistic regressions or neurons together, so that we have 4 hidden units here and 1 finally hidden unit here, and we simply connect everybody and estimate not estimate, but update or learn the parameters for each of these logistic regressions or for each of the neurons. And I showed you that at a high level, if you really aggregate the formulas in a nice way, everything pretty much still looks like a logistic regression under the hood, so to speak. The maths is, of course, different, and it is not just a logistic regression, but something actually more complex and difficult to not estimate, but to train. But it is still remarkably similar, and it really helps us to understand what is going on here at this level.
If you go back to this update slide, yeah, there's a great question by Sina, and the question is, could you use different learning rates for the different neurons?
Yeah, great question, as before. And I know Marcel and myself, we keep saying, oh, great question, great question. It's because they are great questions. I mean, in theory, you could use different learning rates. The question is whether it makes sense, because remember that whatever you do in one layer or in one neuron will affect what other neurons will be doing at a later stage. In, I don't know, in a half an hour or so, we will go and take a look at a very nice and interactive tool where you can play around with neural nets and modify the relationship, so the activation between one neuron and the next layer of neurons explicitly to see how that would affect the whole neural net. And I think from a practical perspective, it would probably not make a lot of sense to regulate each of the learning rates individually. Something that is being done with some optimizers is to have adaptive learning rates. So you would overall start in the early iterations, for example, with great, like large learning rates. And these learning rates then become smaller and smaller automatically. The further you train the model, the more refined you are. And that makes sense, right? Because at the beginning, you would have large steps so that the weights and biases are updated in a very quick way. And once the neural net is a bit more refined, you would then only want to choose smaller steps. So I think the most efficient way to estimate or to train the neural net would be to keep the learning rate the same for everybody, and yeah, for example, decrease it for everybody together and adapt it in that kind of way. But yeah, good question. Is that all, Marcel?
Yep, so far that's it.
Okay, cool. Okay, cool. So let's take a look at deep neural nets. And let me switch back to my slides here. And share my screen again, my main screen. Okay, so we took a look at shallow neural nets, and now let's take a look at proper deep neural nets. And this is how they look like. So the only difference that we make now is that we don't only consider one of these hidden layers at a time and get to the outcome. But now we have a number of them, right? So we taken our data, we had the first layer of hidden neurons, and they all get to calculate an output, and this output is connected to all of the neurons in the second hidden layer, and they pass on their information to these neurons, and they then do the same here with the weights and the biases, and get an output, an estimation, an activation that will go out and affect the layers of the next hidden layer. And this hidden layer finally aggregates everything up, sends it to the final neuron, and we have a prediction here. That's the only difference. How do we train this neural net? Again, we take the same approach as before. We first predict an outcome on the basis of data that is flowing in here. The data flows through the neural net. We get an outcome, and this outcome will of course be off from what the real data looks like. So we calculate how wrong the prediction is, and then using this information how wrong the prediction is, we calculate the derivatives of the cost function for each of the weights and biases in the neural net and propagate this information back here. through these derivatives. And once we have values for that, we can update the weights for each of these neurons. Yeah. So something I want to explain to you is, and let me get to my printer. I'm going to my printer because there is a nice piece of paper. And what this piece of paper does is, and I hope you can see that, what we do here, in particular in the case where we have this binary classification problem, is we estimate a hyperplane through the space. And we want to know, okay, everything above that hyperplane should be coded as a 1, and everything below that should be coded as a 0. Just like, I don't know, a support vector machine, for example, would be just the same. The thing is, if our mathematical space were that nice and easy, a simple linear regression would do the job, and we could calculate a linear regression with 2 variables here in this 3-dimensional space, and that's really nice. But given that we have data that has many, many more dimensions, and what we have is actually, sorry for the noise, is we have a hyperplane here, right? That is sort of crumbled together in a paper ball, and it still is this is still a plane, not in our 3-dimensional space, but in a multi-dimensional space. This is still the same thing. So what do we do when we actually train a neural net? Well, you can think of the weights and the biases piped through any function g. You don't have to use sigmoids in these neurons. You can use different functions, and we will take a look at a couple of them later. You can actually think of it as first as an exercise of the neural net trying to unwrap this piece of paper in this multidimensional space so that it can actually fit this paper into this hyperplane and have it as a decision boundary for the decision. And the way it unwraps that is by taking angles from the data. So it will tell that the neural net will sort of say, hey, to sort of unwrap that, first take this angle, and the bias will give me a certain pull that I need to exert in order to unfold that. And for each of the many neurons that we have here, each of them is sort of a small rule that helps us unwrap this hyperplane. And this is not the most mathematically correct interpretation of that, but it's a good intuition, I think, for thinking about what these neurons actually do. At the end of the day, the last neuron here in our example is a classification, a binary classification. So we are fitting this hyperplane, and all the other weights and biases in the neurons really help us and unwrap that crumbled decision plane that is nested in this hyperdimensional space, data parameter space, and into a really nice and smooth plane that we can work with. Okay, and I think we are 5 minutes early for the lunch break. Are there any questions at this stage?
Maybe like you can go into Daniel's question from before.
Yeah.
If there's no other questions regarding the math. So his question was whether what to do with large data sets with many features and long computation time. Can you say something about parallelization with GPUs, and are there any libraries that support GPUs? So graphical processing units, for anyone who hasn't heard of that lingo.
Yeah, so the beauty, so I think there are 2 elements to that. The first one is that the way we are updating our weights and our biases and everything really lends itself to parallelization, because we can parallelize the task of let me share my screen. We can parallelize the task of calculating a lot of these values and updating them and calculating derivatives in a really nice way. So we can sort them out and give them to different processors. Every of the processor runs a couple of them and then aggregate them together. This doesn't help, obviously, in a small kind of net that we're estimating here, but once you hit, I don't know, 100 million parameters or even more, then it actually makes sense to parallelize these processes. And this is where these GPUs come in, these graphical processing units, which were originally developed for gaming, I think, and then ventured more into this deep learning. And you've heard probably about crypto mining, where parallelization is a big issue as well, where you can use that. So this parallelization is really cool for that, and that's really useful. So this is one element why working with big data is fairly easy or pretty straightforward in the context of deep learning. The second element is the gradient descent, the nature of gradient descent. And this is actually one of the one of the key findings of deep learning in the why it sort of gained traction after this deep neural net winter of the 90s. People understood that we don't have to use all of the data to train these neural nets. It is enough to do stochastic gradient descent. And stochastic gradient descent means you take a random sample from your training data and only pipe batches of the data through your neural net. Okay, so you will find that the batch size is one of the key parameters that you can actually key hyperparameters that you can have for such a model. You take a randomly selected sample of the data, like, I don't know, 16, 32, 64 of the data, of instances of your data, and you pipe them through the neural net and update all the weights and biases with a chunk of the data. And if you do that often enough, you will see that these weights sort of learn enough to converge as well, just like before. At the same time, they are also really nice because they prevent something called overfitting, and we will see that later. A neural net that only sees 16 or 32 data points at a time will find it fairly easy to overfit because it cannot remember the data by heart, right? So it always has to adapt a little bit and wiggle a little bit around, and by that can generalize fairly well. And now, and let me get back to the real answer here that's hidden in my explanations. If you have big data, say, I don't know, gigabytes of data, a couple of hundreds of them, and a very big model with 200, 300, 400 million parameters, it would be very hard to run this on a computer, right? If you would have everything in one go, like you, I don't know, maximize a logistic regression with maximum likelihood. This is where stochastic gradient descent really is powerful, because you only have to throw chunks of data at your model, and it will learn on the basis of these chunks of data, one at a time. And yeah, this is why a large big data sets also make a lot of sense. In terms of libraries, like there are great efforts to do a lot of these things for you under the hood. And in Keras, for example, you can set GPU options in Torch as well. And this is why it makes sense to rely on these sort of high-level libraries that make it easy for you to write up your neural nets. Because people invested time 4, 5, 6 years ago to come up with these libraries. If you want to do this by hand, you can, of course, as well. There is, if you work with GPUs from companies, they have libraries that help you in that. For example, for NVIDIA, you can use CUDA, which is a set of tools that can help you in parallelizing things. You can do that as well, and it really helps you nicely train your net across a number of processors that are in a GPU, right? So a GPU typically comes with 40 or 80 processors, and you can make use of the computing power in a GPU. This is where the speed comes from, right? A GPU, like each of these 80 processors in a GPU, isn't particularly fast, It's maybe way slower than your even your laptop processor. But given that you can parallelize things, you can speed up everything quite massively. So it does make sense. Okay, I hope this helped, and sorry for making you wait so long with your questions, Daniel. I hope this helps answer your question. Okay, then let's all go, and there are no further questions. Let's all go and have a quick lunch break and meet back at I think your time 12:17. For me, it's since I'm here in the UK, it's 11:17, and we see you here in 15 minutes. Musical chairs. Music is off. All sit down. Right? This is we played this a lot in Germany when I was a kid. Reise nach Jerusalem. So and I never understood why we call it Journey to Jerusalem. It's musical chairs in English, I heard at one point. Anyway, we're not here to talk about the deeper cultural aspects of naming things. We're here to talk about deep learning. So what did we cover so far and what will be ahead of us? Let me walk you through that. I'm going to share my screen and you should all be able to see today's learning. So what did we cover? We covered the first two topics already. What is deep learning? You should have a fairly good idea about that already. And if you think back to your selves, when you woke up this morning, did you know how deep neural nets learn? Did you have any idea how that works? Probably not. Now you do. This is amazing. This is really cool. Thanks for being in this class. This is really cool. So I hopefully passed a lot of knowledge from my head into yours about the theory of that. And as you can see, the next steps will all be about experience and skill. So it's really knowing stuff is one thing, but you actually need to do things to get some experience about how they work. And this is what will be next. So we want to get a better intuition about how do deep neural nets actually behave, and how can we actually write code for deep neural nets. And for that, we will use a really cool tool. I really like it for teaching. And thanks TensorFlow people for putting that together. It's called the TensorFlow Playground. I will walk you through it, and then I'll give you 10 minutes to play there on your own. I'll give you some tasks for playing so that you just don't get lost in clicking. Let me take you to the playground. And the goal is to get to know the TensorFlow Playground and get an intuitive understanding about some key parameters and hyperparameters. Okay, so this is the TensorFlow Playground. This is how it looks like. I can't enlarge that. Okay, but you should be able to have that on your screen as well. This is how it looks like. There are a couple of things that I want to show you. So the first thing is the neural net that we can build. And this is sort of what's in that bracket is the realm of what we talked about already. You can see that you can easily sort of add or subtract neurons here and see how that goes. You can easily add hidden layers. I think it's all the way up to 6. And I think the maximum numbers of layers in each neural net is 8. So it's all point and click, really straightforward. That's really nice. Okay, so you can build massive. You can build smaller ones, larger ones, and that's really nice. You can see already that there are weights in between these in these neurons that are going on. At the moment, because we haven't learned yet, we are at epoch 0. They are quite kind of random. And everything we do is, all data is either -1 or +1. And the more positive it is, the more blue something will be, and the more negative, the more orange. And the larger the weight, the thicker the line, and the smaller the weight, I guess, the smaller the line. So it's pretty straightforward. And these will, of course, change once we start training. Then we can choose our activation function. Here they call it problem type. Okay, we can either do a classification problem, which is what we talked about this morning, or we can choose a regression problem here, which is pretty straightforward. Let's start with an easy classification task. And the easy classification task, we could choose here the kind of data that we want to throw at it by clicking here. We will start with this classification task here. So we want to fit a line that helps identify, that helps distinguish between the orange dots and the blue dots. You can choose how much test or training data you want to have, right? So we talked about, Marcel talked about that yesterday in the context of machine learning. So in machine learning, we never care about the actual weights or biases that we estimate here with our neural nets. we can't even interpret them, right? This is something, neural nets really are sort of a black box with that regard. There are some exceptions to that, and people are working on that. It's a very active research field. But yeah, it's really, really hard to make sense of these neurons. And we're not interested in them. What we are interested in, and this is our way of telling whether this is a good or a bad neural network, is whether the predictions go right or wrong. And this is what we check with our cost function already. And this is also how we evaluate whether we have a good model or not. So what we typically do is we take some training data and use the training data to test it. And then we check on the test data how wrong we actually are. And here with this click, you can superimpose the test data, and you can see that it all fits nicely together. You can add a little more noise to your data, and here you can see that there are overlapping regions now where you have orange and blue dots crossing over each other. But let's keep it nice and tidy at a low level. Here you can play around with the batch sizes. There are a couple of other parameters that are not so interesting at the moment. You can play around with them later. What I want to show you is how to run everything. You simply run everything by hitting run. And you can see obviously that, I don't know, after 100 iterations, 100 epochs, 100 times going back, going forth and back, you can see that there is a decision line already emerging, and your neural net learned that fairly quickly, obviously, because it's quite an intuitive thing to do. Something we haven't talked about are the features. We would talk about this more in depth if this were a computer vision class. At this moment, you can think about these features as sort of the capability of a neural net to recognize, for example, a vertical line here. So if you would train a model like this, it can only recognize a vertical line. If you add this horizontal line, it is able to mix this already. Okay, so this is already quite nice and quite powerful. If you add the interaction of them, you can recognize these kind of shapes, which might be actually quite helpful if you have this kind of data. Okay, so here you can see that the neural net fairly quickly learns that kind of stuff. Okay, so I showed you how this works with an easy classification problem. Now let's give it a really, really complex classification problem. Here you can see that we have sort of a data swirl with blue dots going in. And we have a data swirl with orange dots going out. And I want you to take 5 minutes now and come up with a neural net that is capable of estimating that. So activate all those guys here, please. Try to give it a little bit of noise here as well, so that it's a bit more complex. And leave everything up here. The activation function is 10H. The learning rate is 0.03. No regularization right. And then come up with a couple of architectures that can do that. And I would like you to try some things. Try to use as few layers as possible to solve this. Try to solve it with a massive net that makes use of all 6 hidden layers. And also play around with architectures that are sort of a funnel of nets, right? That are sort of large at first and then go further down. And remember this multiple of 2's rules. Maybe you want to play around with that. Feel free to point and click and take 5 minutes. Add all your questions you have to the chat. In at 12:35, so it's 7 minutes. I'll start going through that, and I'll walk you through some examples here in case you have any questions.
Yeah, before everyone gets started, there's one good question in the chat.
Okay.
Whether we can use cross-validation in neural nets.
Yes, of course we can, and we actually will take a look at that later today. Very good question. The code number 3 implements cross-validation, and then we will check that out later today. Good question. Okay, so take a couple of minutes and go wild. Okay, welcome back. I saw a great question from Daniel Bruggeman about cross-validation in the context of time series data. Let's chat about these issues once we talk about cross-validation later. It's a very active research field, as it seems. Let's focus on getting an intuition about the neural nets first. And then Marcel, please remind me if I would forget it, but let's chat about that later, all these cross-validation issues once we do cross-validation. I want to show you, and I hope you had time to play a little bit around and get some intuition about how this works. I really think it's a cool tool. Let me show you some things that we haven't properly covered yet, because I'm introducing things sort of implicitly here. So this is the neural net that I came up with, right? So we have this classification problem, this data swirl, and we can run the model now. And as you will see here on top of the data, you can see two different kind of losses. Okay, so we have the training loss, which is the loss of the loss function or the cost function that we've been talking about so far, and it tells us how far we are off from the real data. Okay, and you can see that training loss go down. And then remember that we keep a number of data sets, the test data, out of the training process. And this is sort of an out of sample prediction to a degree regarding how good this model already generalizes to data it hasn't seen yet. And as you can see here, when I stop the model some 50 epochs in, the training loss starts to get down. Okay? And you can see that the model is already learning on the data it can see, which is this data actually, but we don't generalize really well. Okay? And you can see that here, for example, there is not a lot of data in our training set, but in our test set, there is quite a bit of data, and this might influence our results from the test loss. But let's see what happens if we let that run another 10 or 20 epochs. You see that the training loss goes further down. And at one point, you see apparently that the test loss is going down as well. Okay? There is a really nice way of visualizing the areas where the model would predict a 1 and the model would predict a 0, which is really cool to follow here. And you can see that our test loss now goes down as well. So we see that that the model is actually learning quite well. And you can see the areas wiggle a bit where prediction goes wrong and right. You can see that in a lot of variation going on here in our training loss and in our test loss. And at one point, if we let that model further run and run and run, you see that training loss goes down and down and down, and we are getting closer and closer to this area where the blue dots should be all connected, and the orange dots should be all connected. And at least in the previous run with this particular setting, it all came to a stable solution, and we can see that it's sort of getting there. Yes, and yeah, in the previous run, the test and training loss even converged to the same level. Okay, so we can see a number of things that are actually going on here. You can see the neurons that give the features we have. We now have low-level geometric forms and shapes here. So basically blobs or crosses or something, and that are easy abstractions from this data. And the higher up we go, the more complex do these geographic representations become of these geometric representations. Okay, so these neurons can actually make use of the shapes that these neurons have learned and can build together more complex things. And again, these neurons will do even more complex things. And as you can see, these two neurons here will themselves have different ways of representing the data, which is quite interesting. Okay, so let's see how a flat model performs with maybe 2 neurons here, and if we let this model run, you can see that it has a much greater difficulty in probably recognizing these at first, and ends up at a point where it really cannot generalize so well anymore these shapes. But it still keeps learning, and the training loss goes still down a bit, and even the test loss goes down. And it keeps getting closer and closer to a solution, but doesn't really nail that. And if we make this now more powerful, all the learning should be actually way quicker. Let's go and run this. And as you can see, it takes more epochs, right? The computer that is actually training that isn't as quick anymore because there are so many more parameters, and then training time becomes something of an issue here. But the capability to generalize is much better, of course, simply because we have more neurons that are at play here. Okay, this already gives you some nice intuitions about what is going on here. There are a couple of hyperparameters that are hidden and that are sort of presented here as if they were nature given, which is different activation functions, regularization, the learning rate. We talked about that already, of course, and you can play around with the learning rate and then see what that gives you. You can also run regression kind of problems, and I thought that is a nice regression problem where we have areas that are blue and areas that are more orange. And if we run a model on these data, you can fairly quickly see that the model then learns the areas where it should predict blue and where it should predict orange. And the test loss is almost as the same as the training loss, simply because we added no noise here. Now, if we run the same thing again with a little bit of noise, we can see the test loss, the training loss. Yeah, it's still easy enough so that the model can learn it. But if you amplify the noise here, you would get different results. Okay, so I think it's a great tool to have a first sight and first intuition. Oh, there is a question, I think, Marcel.
Yep, that just came in.
Yeah, so can we say that to understand the data better, we trade off with the time and network complexity? Also, does greater the number of neurons have something to do with overfitting the train of the train of the data? Yeah, so this is basically where I want to take you, Bita. Great question. That the more powerful a network, the more easy it will overfit. But I will sort of nicely bring this, or make this insight sort of trickle in your heads, hopefully, for the next 45 minutes or so. We will definitely get to that, all the problems of overfitting and all this. Let's first, in the next step, understand in a bit more of a systematic way the kind of parameters there are that we can actually play around. For that, I want to bring you back to the presentation. Okay. So you got to know the TensorFlow plane, the TensorFlow plane, well, sorry. And you recognize some key parameters and hyperparameters. Let's take a step back and think in a bit of a more rigorous way about, what are actually parameters and hyperparameters, and let me walk you through a couple of insights here on the slides. So what are parameters? Well, parameters are those variables, if you want to, that can be optimized during training with the training process, with the training algorithm. So it's our weights and our biases. These are the parameters that we actually are optimizing with our optimizer here. We took a look above all at stochastic gradient descent or gradient descent. Then what are hyperparameters? Well, hyperparameters are actually parameters. They're also variables, right? We can play around with them that can be, or that need to be specified before training. So, for example, it's the number of hidden layers, L, so how deep is your model, and it's the number of hidden units, so how many neurons will you actually have in one layer. It is, for example, the choice of the activation function. So far, we took a look at the sigmoid function. There are a couple of other activation functions that we could also use. It's the optimizer that we could choose in order to optimize. So far, we took a look at gradient descent. There are a couple of others. The learning rate, the batch size, and this is just to name a few. And if Marcel had made a big point about hyperparameters in the context of machine learning yesterday, it is even more relevant here in our context. As you saw, just playing around with a number of layers and hidden units gives you, a vast amount of architecture possibilities that you could choose from, and that you would probably want to check if you want to make a prediction. So hyperparameter tuning is an important and a massive issue in the context of deep learning. And if you think through that conceptually, what tuning a model actually means, right? So what do you actually want? Okay, so at the end of the day, you will have some data, and you know that you want to train a model in order to make out-of-sample predictions, right? So you might have data where you know the labels and you want to use that as training data. And you have more data, maybe another spreadsheet, or even a data stream, right? Think of data that might continuously come in through some measurement, for example, I don't know, a Twitter data stream, or what else could we have in a social science context? Behavioral data from a panel, data from mobile phones where you measure people on every day or even every hour or so. So you have a data stream that is coming in, and you want to annotate this data stream, like by classifying certain variables, by labeling certain things in an ongoing basis. So you want to solve this prediction problem, and you have an optimizer that helps you optimize your parameters given one model and one data that you have. And that's an easy problem, right? Because we know how to optimize, or how to learn from data. That's really straightforward. However, that's not everything we need to do. We not only need to learn the parameters with gradient descent that we saw, we also have to optimize our hyperparameters. So the hyperparameters that actually determine how our architecture, how our model looks like. And this is a hard problem because we need to come up with an algorithm over a probably very large hyperparameter space. So why is tuning actually so hard? Well, it turns out that typically you can't really you can't calculate the derivative of your objective. So if you can't calculate a derivative, it's really hard to optimize it, because you cannot determine the minimum or maximum, right? You can only evaluate things, but then you're left there. On top, evaluation of learning is expensive, as you already saw in here in this very simple neural net, right? Where you have say 6 hidden layers and 8 neurons in each. Each epoch already takes a little bit of time, say half a second or so, right? This is quite a bit of time that goes that goes down the drain, and it can easily go up to minutes, half hours, or even hours per epoch. And if you have to run a model for, I don't know, 100 or 200 epochs to see whether it makes sense with a hyperparameter setting, just a grid search over, I don't know, 2 to the power of 3 or 2 to the power of 4 different hyperparameter settings is already very, very expensive to do. So the evaluation of your hyperparameters is very expensive. And in deep learning, this is particularly bad because your space of hyperparameters is very large, because you not only have to control 1, 2, or 3 parameters, you have to control so many more parameters. And this is why, it's a hard task in this context. This is why training good deep learning models is a very expensive thing to do. Just the energy that is used for really good models, and that's without the hardware investment, can really generate tremendous costs here. So deep learning, if it is done at an industry level, can actually be quite challenging. And the solution to that hard problem is a very active area of research. So you would typically try a number of different hyperparameters that are sort of based on best practice, because there are often no real mathematical proofs in why certain things behave better in one way or the other. And the way you would typically try these different parameters is either to be systematic in a grid search. You can also do a random search, but in like the most cost-efficient way in terms of saving training time is still a very active area of research. It's something that's actually really exciting, and that will be really useful if we actually tackle that problem. So we talked a lot about a number of these hyperparameters already. Okay, so you know the number of hidden layers. You know one optimizer, which is fair enough at this stage. We talked about the learning rate. Batch size is pretty straightforward, right? It's simply the amount of data that you throw in your stochastic gradient descent. And one thing I want to talk about with you now is the choice of the activation function, if I am right in remembering what I put in here. Okay, so activation functions. This is actually really exciting. The most common ones are all implemented in the standard packages like Keras or Torch. So when neural networks were invented, they were invented in a way that we went through them today. Everybody was using the sigmoid because everybody thought, well, we want to have an input that can be infinite here on the left and infinite on the right, and we want to compress everything between a value of 0 and 1. And this is why in the early days, until say the 80s or so, people were using sigmoid function. Then in the 90s, people came up with the idea, well, as a matter of fact, it would be nice if we could make use of the whole range between -1 and +1 as output. So let's use the tonnage instead. And people were trying a lot of things with the tonnage. And both of them are still used in this context. But something that happens easily here is the problem that is called a vanishing gradient. And let me walk you through what that is. So imagine we have a neuron, and for some super weird reason, because the network isn't stable enough and it isn't well trained, it gets an input at say +20. Okay, so if you think of this line to continue and approximate the one here on the very top, you will see that the value, that the weight that is corresponding here might be quite a large one. So the next iteration, the learning that can be done on the basis of that will be a very small one neuron up the chain, right? The change that the neuron can make is only very infinitesimal, because we're talking about a very small change here in values if you would actually change the weight that is according. So ideally, you want to be in an area like your learning is efficient in the area, say, between -5 and +5 for a sigma. But anything other than that would be really, really bad. It would be really problematic to feed into your sigmoid. And this vanishing gradient problem can be really, really problematic the deeper your model is. And it's actually one of the main reasons why the whole research around neural networks broke down or got way less attention in the 90s and early 2000s, because people didn't know how to control that problem, actually. And the big invention, no, where is it? Yeah, sorry, I was mixing up things here. This is how I wanted to continue. The order got a bit mixed up. The big invention, and it sounds super simple, but it changed a lot, was to say, hey, let us use a rectified linear unit. Okay, so how does a rectified linear unit actually look like? It is important that you have a nonlinearity as your function here, and the nonlinearity looks like this. It is the identity for all values that come in between that are higher than 0. So if you get a 5 in, you will get a 5 out. If you get a 10 in, it will give you a 10 out. But for everything lower than 0, it will cut this off and always output a 0. Okay, and this invention actually helps dramatically first to avoid the vanishing gradient problem, because here you have now half of the function where this can't be an issue anymore. And at the same time, it really helps you speed up the calculation of your derivation, because it's simply the identity over to 0, right? That's really, really easy here if you compare that to what we did here with the sigma. So that's actually really, really cool and really helpful. And this ReLU changed a lot when it came up in the early 2000s. Then people kept improving and tinkering on the leaky ReLU a little bit. The first improvement was to say, well, maybe we want to still allow a little bit of learning that is going on here because it might be a bit quicker. Then there's something called the ELU, which sort of gets rid of this kink here and has sort of a curve that is going down here. There are little refinements, but the big game changer in the whole deep learning literature was this rectified linear unit. It is really simple now, 15 years past that. But when they came up with that 15 years ago, yeah, I don't know. It's shockingly simple how like solutions, once you got them, can be shockingly simple in some contexts, and that's really powerful. So let me see. Yeah, this playtime is certainly wrong, but I'll get to that in a second. I want to show at the whiteboard why we need activation functions. Let me check on the chat. Okay, cool. Let me check on the, I'm sharing my screen again. Why these activation functions are actually really, really useful. Okay, so why are these activation functions really useful? And let me make some space here so that we talk about this line first. Okay. Remember that for any level that we might have in the data, for any hidden level, we have a couple of weights for each neuron. We have the data, we have the biases for this layer, number one, and this will give us a output Z, or also the activation for this particular layer. We also have a second layer here, and let me bring that up for you. And in the second layer, we take in these activations as new data. And in the second layer, we have biases and weights as well, and they generate us Z and a certain A. Now, if we did not add a nonlinearity here, right, but simply take this A directly from Z, we could rewrite everything in the following way. We could replace this A1 with this term here, okay, and rearrange these things a little bit. And let me show you how that looks like here, because I don't want to give away the punchline. And we could say, hey, if we use A1 in here and bring this term in here, we can rearrange this, this formula a little bit and have A2 equals the weights from the second layer here times the weights from the first layer times x, this guy here, plus the weights from the second layer here, plus the biases from the first layer here, this guy, plus the biases from the second layer here, actually. Okay, and we can summarize those again. Okay, so we can say, hey, these weights are simply weights prime. This is the x, and this is sort of a bias term that is going on here without any touching any bias. And what we see is that it basically boils down to a regression again, right? And this is not what we want to have, because we lose all the power that we have through the updating with a nonlinearity that is going on in there, and everything will actually collapse to this regression set. This is actually the reason why we want to have an activation function that helps go around this problem, and that we can simply use the A1, edit here, and then rearrange the equation and come up with the same problem. We want to solve something, we want to learn something, and not simply go ahead.
There's one question in the chat. The last B here, is there a 2 subscript missing?
Yeah, sorry.
Superscript. Yeah, great observation.
Yeah, I made that on purpose just to see whether you will pay attention. No, sorry. So seriously, this is yeah, it's a B2, of course. Yeah. Okay. Then let me share my normal screen again and see where we are. Yeah, cool, awesome, looks great. Let's go through code number 2 now, and you guys take a look at some more code. And what we will be doing is we will revisit the code that we had in the very beginning, and then you get to play with that for 10 minutes through a number of exercises that are prepared for you. Okay. You should all be able to see that. So that's code number 2. Again, we install the packages, the Keras library here. It should be pretty straightforward since it's only one package, and it should be all on site already, and it doesn't take a lot of time. Then we go on and load the MNIST data set, and this time we will generate a validation set as well. So not only a train set, but also a validation set and a test set. Okay, so if you want to do proper hyperparameter tuning, what you do is you take some part of the training set and you see how good this works on a validation set. Okay, and this helps you evaluate and choose your hyperparameters. Remember that hyperparameter tuning is actually a nested problem. Okay, so our training data is actually helping us in the optimization problem, and our validation problem is helping us in choosing the hyperparameters that are around there. Okay, so this means that if we use both the training data and the validation data to train the model and also choose the hyperparameters, information from both of them will actually flow into the model and into our predictions, right? So if you want to really test something out of sample, we also need to make sure that there is a test sample that is withheld and that is remaining outside of this whole process, and staying out of all this. And this is what we're doing here. Okay, so we select the images, and the train images. And on the basis of the train images, I am selecting another 10,000 observations to do a validation set. And I generate test data and arrange the labels and convert the labels of the train, the validation, and the test set into, again, these labels that have one-hot encoded labels. So it's basically 10 dummy variables that give us an indicator whether there is a digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in there. Okay, and this is all happening in one go. You can go through the code in detail at your own pace at home. What I want to do now is I want to show you first how it works, and then I want you to go through a number of exercises for some time to learn how to tune hyperparameters and how these hyperparameters actually matter. Okay, so let's go and understand the simple network architecture. And again, be amazed about what you know by now already in comparison to 4 hours ago. So we call a Keras model sequential function. And the first thing we do is we want to add a dense layer. And we add 32 neurons in this dense layer. This is the first hidden unit. Okay. We give them an activation function, and here we give them this ReLU activation function. Remember this cool thing that they invented in the early 2000s. And then we need to specify, but only for the very first layer, the input shape, so that the neural net knows how to construct this basic layer. And then we pipe that into our final output layer. And here, since we have 10 vectors that we are predicting, 10 variables, so to speak, we need to have 10 units for that. 10 units who each decide 1 and 0, and an activation function that is basically, it's called a softmax activation function. It's basically a sigmoid, but for multiple cases. Okay, so whenever you choose to have more than one category, make sure that the units match them and that you have a softmax category here. So this defines our model. And if we type network, we can get an idea about how that looks like. Okay, so we know that with this kind of model, we already have 25,000 parameters in here that we are estimating in this dense unit, which come all from the data and the number of nodes. And we have 330 in this final output layer, which comes from the activation function from the hidden layer and the number of neurons that we have in there. Then we compile it, and in the compilation, we need to set an optimizer. We use RMS prop. Not so important for now how that works. It's basically something similar than gradient descent. We use a loss function, which is a categorical cross entropy. It's basically what we saw for the sigmoid function, but for this multiple category context. And we have to use a metrics that we want to measure how, as a means of how good we actually are in our estimation. And here we simply take the accuracy of the predictions. You can use an F1 score or whatever you want to here as well, but this is what we're observing. And then we want to train, and for the train, we have to provide the training images, the training labels. We need to tell Keras how long we want to train for 20 epochs, and we want to give the batch size. And batch size is the amount of data points that we want to pipe in at a time. Okay, and then some validation data, the validation images and validation labels, and we can train that, and I think it should take like 20 seconds or so, maybe 30 seconds here. If you do that in R on your own computer, you can follow the training much better. Here in Colab R, yeah, it's a bit more the magic ball kind of approach where you have to wait a bit. But once everything is done, after 20 seconds, we have stored it in our history object. And we could, for example, again, let me add. We could plot that history object a nice Keras plot that already helps us in taking a look at how that looks like. Okay, so you have the training data in orange, that's the accuracy, and you have the test data in sort of greenish. I hope you can see that and distinguish that. That's just, yeah, not so clever maybe for people who can't distinguish color so well, but that's the default in ggplot here. But you get the idea. And once you are happy with the hyperparameters, so this is where hyperparameter tuning would typically happen. Once you are happy, you can evaluate everything using the evaluate function, and you get a loss for the true out of sample, and you get an accuracy for the true out of sample accuracy. And you can use predict classes to get the classes that the network is actually predicting on the test images. Okay, so you give the model some test images, and you get in return the classes that it predicts. Okay, this is how it works. Now here are a couple of exercises for you to do, and it should be pretty straightforward for you to try that. Let me see how far we are in time. I'll give you 10 minutes to play around with that, maybe. And yeah, I'll give you 10 minutes until 12:20 or 1:20, I think that's in your time, right? So 9 minutes now. Play with that, and it's pretty straightforward. I put everything down. In the first exercise, you can play with different network architectures and see how they behave. Make sure that you always follow this routine, okay? You first define a model, then you have to compile it, then you have to fit it, and then you can get a max value and a plot from that. And you can input different nets, right? So you would execute this block here, and then this guy here for training this model that is very small, a narrow and shallow net. You can use a narrow and deep net, a wide and shallow yet, a wide and deep net, and so on. Don't forget to compile and evaluate always. Then exercise 2 is different activation functions. You can play around with them and see how they work. So use sigmoid functions, the 10H, and the ReLU. You can take a look at different learning rates and see how they react. I show you how to implement that here. The same for different optimizers and different batch sizes. Yeah, the big takeaway, and you will take more than just the 10 minutes we have now, will be once you run that on your own at home in half an hour or so, a big lesson to be learned is how sensitive these neural networks are. Okay, so really, depending on their setup, you can get to very different results. But I want to give you some time to try that on your own. There is a question in the chat. Yeah, okay, we've done that. Okay, cool. Then enjoy. We'll be here at 12:20 in 7 minutes. Go and run this code a little bit for you. Okay, everybody, welcome back. I ran exercise 3 here for you on my notebook, and just walking you through some results. Okay, so I gave you the model that you could use. So you had to execute this bit, then compile it, and then use this evaluate chunk to see what's going on. And you can see that you got a validation accuracy in the like the maximum validation accuracy, the best model here from the ones you ran, we're at 0.983% correctly predicted. And you can see that sort of that the training accuracy goes up and is a little bit higher. The validation accuracy still goes higher, and it sort of has an upward trend. So you might want to run it a little bit further, maybe 40 or 50 epochs, and see whether this improves your fit, actually. Now, if you do the same thing for a learning rate that is at 0.01, the picture already looks quite different, okay? So you get a weird accuracy that doesn't go higher than 11 or 12%. You have an out-of-sample accuracy that doesn't work, and the maximum validation accuracy that you have is only a 0.112. Okay? And the only thing, literally the only thing that you changed is changing this learning rate from 0.001 to 0.01. And you will find similar results for all the other hyperparameters that I gave you. If you crank that up still further, this learning rate to 0.1 in this example, you can see something fairly similar, right? We'll flat out at like once everything is learned at sort of this 0.12, 0.115 training and validation accuracy, and the loss sort of flats out as well. The neural network cannot learn anymore because you just changed one hyperparameter in the wrong way. And this happens with the other hyperparameters as well. This is the important takeaway is here that you need to do a lot of hyperparameter tuning if you want to make sure that these models work well on the data set that you gave them. Okay, let's take a quick 5 minutes break, and we are back at 12:27 or 13:27, 1 o'clock 27, and then continue with the last quarter. Okay, everybody, welcome back. Let's go and check out the last bit of today, and it will all be about.
So there's 2 questions, I guess, that make sense to answer them in one go. So via YouTube, the question came in, how do you determine the best number of layers? I guess we had that earlier in the morning as well. And the second question is regarding hyperparameter tuning, would you recommend working with autocarers for deep learning to avoid manual tuning?
So both, again, great question. So the right number of hyperparameters is determined just as any other hyperparameter by trying out what works best. And this is why we do all this setup with training them on a validation set, seeing what works best for the validation set, and the best performance will then be our final model. We can then check how good it actually is on an out-of-sample prediction by running it once, and only the final model on your test set, right? Because that's ultimately what you want to do here. Regarding autocarers, you can of course give it a try and make sure that you understand what is going on there, and not just use it as a function, because it's always great to look under the hood and see what comes out there. An alternative way, if you want to have more control, is to simply explicitly write out everything on your own, and be very specific about the kind of hyperparameters that you want to pick or that you want to tune. But as I said, this is all still a very active area of research, and something that, if we get a handle on this in a better way, will really help us in estimating or sort of training these models in a more reliable manner. So all very good questions. Okay, the last thing, tuning, tackling overfitting. So I showed you how to play around with hyperparameters and make the model better, but it is easy to fall into the trap of overfitting. So what is overfitting? Well, so far we thought we are in this area here, where we, on the one hand, would fit a regression line here in a very bad way, of course, to some data. Overfitting is the other opposite. It would be fitting a hyperplane that is so hyper accurate around the data that is at hand that it's really hard to generalize from. So ideally, we want to hit a smooth area where we minimize the mistakes, so that new incoming data that, of course, will be noisy might still be generalizable enough to fit. And this means in practice that your cost functions on the training set and on the validation set, they should be as closely together as possible. So how do we avoid overfitting? So what happens if we are in that area? Well, one thing is, of course, you can downgrade your model and make your model a bit worse, but that's not really cool, because we want to have a really powerful model that makes the most of it. And something that came up again in the early 2000s, which is insanely simple if you think about it, is called dropout. And dropout learning works as follows. You specify a certain probability to eliminate a node during one particular pass. Okay, so you randomly eliminate here, for example, this node and these 2 nodes, and you learn the model with now only 3 nodes here, 2 nodes here, and 4 nodes here in the forward pass. And you backward, you do the backward propagation of your cost function here, and update your weights accordingly in each of the layers, but only for those that you have actually put into. Okay, now the next iteration comes, and it's not these 3 nodes that drop out, but maybe it's this node and this node that drops out. And this way you introduce or you force the network to be a bit noisy and to not see every time all the data. And that way it is sort of generalizing a little bit better than if you would have all the data go through all nodes all the time. And it can be particularly useful for layers with very many parameters, very often used in computer vision, for example. The cost function, of course, J is no longer properly defined, since you have different models basically that you're estimating each round. Okay, so every time it's a little bit different. So how do you actually develop your model? And it is a lot of engineering, if you want to, a lot of rolling up your sleeves and trying out ideas, coding things, running, checking results, and then improving upon these results. So it's very experimental. Some good advice is to try to use 2 to the power of x in your model architecture and also in your batches, because sort of the width of the net, if you have, I don't know, 64 nodes that collapse into 32 nodes, it makes a lot of sense if you think through that in terms of what each of the nodes can pass on to the next one. Like think of, I don't know, 49 in one and 17 in the next layer. This really doesn't make a lot of sense. The overall goal of developing a model is to strike the balance between over and under fitting. Okay, so if you see that both your training accuracy and your validation accuracy is still going up, you know that, hey, you can improve that model by running it longer. If you see that both of them are still overlapping, you can see that, well, maybe you can make the model a bit more fierce and a bit more powerful and edge it more towards overfitting. And overfitting would be seen by a training loss that is way to the roof and that outperforms the validation performance. And if the cost function for training and testing are the same, as I said, then try to make a better model. If you run into overfitting, use regularization and introduce this dropout. Okay, this is something you can do. So we have final playtime now, and I'll give you another, I don't know, maybe I'll walk you through the code number 3. We have a quick chat, and I'd give you 5 minutes to either pick and try whether you can get one of the models on the TensorFlow playground into overfitting, so that you can now use the capabilities of TensorFlow. Let's see whether that works. So here you can introduce regularization. Damn it, it doesn't have dropout regularization, but only L2 regularization, which just take it as another technique of regularization that helps you to fight overfitting. I can run you through that, and if we had more time, I would have. It's fairly similar. It's like you can think of it like a dynamic way of eliminating certain nodes depending on your training progress. You can play around with that here and then introduce regularization and see what it does to your data. The other thing I want to do with you is to take a look at code number 3. And why do I want to take a look at yet another piece of code? Well, it's a new code that takes a look at house prices from Boston. So it's more like a regression kind of problem that you are used to, that you typically know from social science. You can experience the effect from hyperparameters here as well, and learn how to balance model performance versus overfitting. Let me run you through that code quickly. And this is how it looks like. Okay. So the goal is, again, the goal, as I mentioned, is to predict house prices in Boston and Boston suburb during the mid-70s. Okay, and it's simply a classic data set that is in there. So the house prices can, of course, not be compared to what's going on today. But yeah, these are the house prices. As you can see in a second, once Keras and in particular ggplot2 is installed, the data set is a fairly small data set. So we don't have this scenario with 70,000 observations in the training set where we can easily branch out 50,000 for training and then another 10,000 for validation and another 10,000 for testing. We now have to work with data that looks much more similar to what we are used to in social sciences. We want to normalize the data. Remember that I told you that, and now you understand why. We want to have values for each of our features that are between 0 and 1. And the reason for that is we want to be close to 0 with all the values, with all the activations that we get ideally, because then learning works actually really well, really nicely. So it is great if we already enter training data here that is between 0 and 1. It is a little bit like doing a maximum likelihood estimation, and you just have normal variables, and you enter, I don't know, GDP values for that are 2 million, 2 billions, 5 billions, 100 billions, whatever, and you can find that your MLE algorithm is working well simply because out of a sudden there are massive values in your data that make the optimization really problematic. So neural networks really like it if you normalize data before you actually show it the data here. Then the way it works is in principle exactly the same as before. The difference now is since we only have 400 observations in the training data, right? We have 13 variables and 404 observations in the training data. We can do something that's called cross-validation. And here we use a like a k=4 validation, simply because it takes out a little bit of randomness from our data. Since we only have so few, the results might largely depend on the kind of data it sees. So it is, yeah, it can be a good idea to embed that in a k-fold validation. So we write a quick function where we first define the model and then also compile the model. That's the first function that we have. And I don't want to walk you through all of the details here of this k-fold validation, but we define the number of folds. We define the indices to be able to, again, generate validation data for within the fold, the number of epochs that we want to train, and we want to collect all the histories that we're actually interested. And so the validation mean average error histories and all for the test data as well. So yeah, we can simply execute that and see how this goes, and calculate validation scores and generate plots from that. And you can see how this cross-validation works. It's your own turn to keep building models and adapt models in a way that you think is a good idea. So you can change the units. You can easily simply add new units in the way that we had. If you want to add a dropout layer, and this is the way how you do it, at the dropout layer immediately tackles the dense layer before and just the dense layer before that. Okay, so if you want to do dropout, you can do that. You would typically do that at a later stage, maybe 2 stages, like in the middle of your deep net and at the end. This is how you typically do it. Typical probabilities are somewhere between, say, 0.2 and 0.6. It's again a hyperparameter that you can tune. Yeah, see what you get out of it. And once you are happy with the result of your hyperparameter tuning, you can do your out of sample prediction, and this is how you do it. So yeah, take 5 minutes to play around with this code. Feel free to expand on playing around with that tonight. It should all work smoothly here in Colab, and meet you here back at, yeah, take 8 minutes at 13:50, so at 10 to 2 of your European time. Here in the UK, it would be 10 to 1. And if there are any questions, seriously, keep them coming. I'm more than happy to help you out. Okay, everybody, welcome back. Let me share you my screen one last time.
There's an excellent question, and I guess you will touch upon it like in the last bit. And it is, how much better is the performance of neural nets? And is this worth the cost and loss of explainability versus less black box models?
Yeah.
Bruce asked this question. Yeah.
Really, really cool question. I really like that one. Let me walk you through very quickly through what we see here first, and then I'll tackle Bruce's question and also the one that we had fairly early on about cross-validation in the context of time series. Yeah, as you can see here, we do get a nice validation mean average error, and it still goes down for both the epochs. So it might make sense to keep training that and see how this might behave. This is the same, just different visualization. And certainly this is a fairly weak model here. So you can definitely improve the model and make it better and get better prediction results, and you can easily see that. Now let's tackle the question about the explainability and the power of these models first. Something that, like when I started working with neural nets, is that they can be really quite powerful for problems that we first think are quite intractable, right? Think about this MNIST dataset and think how you would try to solve that with a standard econometrics or statistics toolkit, right? It would be really hard to wrap the head around that. And we saw in the very first code, the code number 1 today, that just a shallow net with 512 neurons manages to solve this problem surprisingly well. Okay, so they can be really powerful for some applications, and it is really cool to see how good they are. There are two things that are element to the answer to Bruce's question. The first one is, I think it always depends on the amount of data you have at hand. So in most medium-sized data problems where you have a couple of thousand observations, other machine learning models might make it more straightforward and might make a better prediction. Okay, in particular in areas where you have defined features, like in this code number 3 regression setting, where the features are already obvious. Okay, so we hand-picked the variables like crime rate, property tax rate, number of rooms, and so on. So we know what's going in, and why not just use a regression tree or random forest or anything that's really powerful for predictions instead of a neural net. In particular, if there's fairly few numbers. So that's the issue at case. So neural nets excel in those areas where the things that you want to estimate, the distribution, so to speak, that you want to estimate, or the room in which you want to unwrap your hyperplane. Remember the example with a piece of paper, right? Where this is very high dimensional. And since we have so many parameters, neural nets can be quite good, I think, in helping make sense of the data that's coming in at these scales. So I think this is how I would respond to Bruce's question. Sorry for giving you yet another, well, it depends answer. It really depends on what you want to do, the data you have at hand, the challenge that you're facing. You have to try it out. My take on this is, for a standard regression problem, uses a standard regression model and see how good it is. However, it can improve predictions in some areas to in fairly important ways. Right? So if you think of it from a practical point of view, an accuracy of 95% in a model, that sounds quite a lot for us social scientists, right? And this means that in practice, if you have a software that helps you label an incoming data stream, it will be wrong in 1 out of 20 cases. Now, nudging this up to 99% will make you wrong in only 1 out of 100 cases. So even though you only in absolute terms have a 4% improvement, it really helps in the user experience of that kind of software. So that's a thought to keep in mind. Going back to the cross-validation problem with time series, well, this is actually this is a real area of research, and maybe the exact kind of time series prediction is not best dealt with the fairly simple neural net that we took a look at so far. We will take a look in a second at a couple of other architectures that might be more appropriate. Again, the short answer to it is it depends, and this is a very active area of research, and how exactly you want to funnel in which kind of data into your cross-validation set, whether you just want to draw at random or whether you want to control that. As far as I understand it at the moment, I'm not a time series expert, I must say. This is still ongoing research. I think there's another
just came in. So is the dropout method that you talked about similar to using the lasso in machine learning? So
yeah, so that's exactly our L2 regularization at the end of the day. So what this does, so there are some comparisons, of course, where this makes sense. Dropout is really brute force, right? And again, it was a massive improvement of predictions that people had when they used that, because out of a sudden they could build bigger models because these models wouldn't overfit anymore. And this was a very handy and really very useful way of doing that. It's very characteristic for the kind of literature that develops these neural networks, because it wasn't derived from first principles. I'm pretty sure it was somebody trying out, hey, why don't we just randomly eliminate some of these neurons and see whether that works or not? And only later do people understand the deeper mathematical concepts and bridges to all kinds of other techniques that are out there. I think, yeah, that would be sort of my take. Okay, then last bit. I promised you we will take a look at some more things. So is this the beginning or is this the end? This is how I titled it, and obviously it's not the end, right? So what we talked about today, and this is how I designed this class, was to give you a really solid mathematical understanding how neural networks work, and how they are related to logistic regression in one way. And on the other hand, I wanted to give you a first intuition about how to work with them, get an intuition of how challenging it can be to actually use them for prediction. And let's now take a look at all the beautiful Lego houses, cars, and spaceships that you can build with them. And you can distinguish very roughly between sort of three challenges that are being dealt with using deep neural networks. The one challenge that you might have is you want to process sequences. Okay, you can have different architectures. The architecture that we were working with mainly is a one-to-one architecture, where we have one data set that's getting in, and we have one output error. You could also have architectures and build them in Keras where you have one data set and you have two labels that are coming out at the same time. Right? So you might, I don't know, for example, you can do a sentiment analysis, and you can score happiness and sadness at the same time as, I don't know, whether it belongs to a certain topic or not. And you can have this all and annotate that all in one go with a neural network. You can have many-to-one labels where you have different data sources, like, I don't know, audio and video data, for example, or image data and text data, and get one label. You can have all of them at the same time, and you like this, or you can have them sort of a sequence processing. All these many-to-one, like many inputs, can also be different times sets, for example, that can come in. And the question is, how can we deal with these kind of sequences that come in that depend on each other, like, I don't know, states and Markov models, for example, might be another. Latent states could be something that you're interested in. And one simple way of doing that is something called a recurrent neural net. The way you can find that often is like this. So you have a vector of time-dependent observations that is coming in. You have a latent hypothetical space that is in here that predicts an outcome at t, but that's also self-reflective. So if we unroll this, and this is how it looks like. In t-1, you have data that is coming in, you have a latent state of the model, and make a prediction for t-1. Then you pipe that latent state already into the current state, and you add new data from today and predict something. And here in this medium stream, so to speak, the model keeps carrying information from past times and keeps updating them directly in here. Okay? And this can help model performance. There are ways in being a bit more fancy in here, and that can help you, I don't know, shortcuts where things in the long memory of the neural net, like 50 or 100 epochs before, can be fed forward to certain neurons. There are all kinds of architectures that you can work with them, and they can be really powerful in sequence forecasting, so all kind of time series applications. And recurrent neural nets are your entry label that you can Google if you are interested in these kind of models. Then there's a class called convolutional neural nets that are very common in visual data analysis. And these models already existed again in the 80s and 90s, I think. And the way they look like is a little bit like our TensorFlow playground example, actually. That might be something really useful that just crosses my mind. So in a convolutional neural net, you have filters like these, okay, where the data is coming in, and you have a filter that you want to apply to a certain image. And with this filter, for example, if you would take a fixed filter, you could go over this image, pixel group by pixel group, and move that in here, and see whether you detect such a vertical line. And for example, if you move that here on the top, at one point you detect a vertical line, right? And this would be mapped into one of these features, into these feature maps. You can have others for horizontal lines, and this would be mapped as well. Now, the old school way of doing that was with these fixed feature maps that have predefined functions, like here, right? Horizontal, vertical, these kind of lines. The modern convolutional nets estimate these filters actually along the go, so that you can build both filters and feature maps up at the same time. And you then have a series of features, filters, layers like that are going deep into a neural net. And at the end, on the very top, you would have 2 or 3 layers that are fully connected in the way we stack them, and have them there on top. And at the end of the day, make a classification. For example, is this a picture that contains a robot or not? And just as these recurrent nets, CNNs are already built into Keras or Torch or anything else, and it's pretty straightforward to actually use them. And really cool, and it's also quite powerful. So one of the big advantages of working with neural nets is, again, in comparison to machine learning, that whenever you do not have predefined features, but images or sounds or I don't know, language, music, whatever kind of data you might have, these neural nets make sense of the data on their own, and you don't have to predefine features like variables or anything else. Then there is something that myself a little bit, and above all Marcel has been looking into, and it's actually the topic of his PhD. So he is the expert on GANs. And GANs are basically generated as adversarial nets, and it's actually a very cool. It's a very cool model. I really like it. It was invented by a guy called Goodfellow in his mid-20s or something. And the way he described the invention was he came home from a party. He had this idea about how to code that, and he was so excited about that that he went home from the party, implemented it, and tried to see whether this works or not. And what it does is it is basically a game between two neural nets, two deep neural nets. One of them is a generator, and the other one is the discriminator. And they both play a game with each other. And you can use a metaphor of a band of criminals who want to counterfeit money, and the police who try to catch them to explain what's going on. Okay, so imagine you have a junior police officer at the beginning and a junior criminal who are not very good at their job. So they are both fairly naive professionals. And the guy who counterfeits the money will make a first version of I don't know, a 10 euro bill or something, and he will give it over to the policeman. And the policeman, she's the only one who has actually access to the real data. So she will take a look at a real 10 euro bill and the counterfeited one, and will try to distinguish whether this is real or counterfeit. Now, in the cost function, both of these actors have different goals. The goal of the generator, the person or the network who generates something out of noise, is to make the discriminator maximally uncertain. So the criminal wants to achieve that the police cannot distinguish between a real and a fake 10 euro bill. While the police obviously wants to be as sure as maximal that this is real or fake. And what these neural nets do is they play this game back and forth and back and forth and back and forth, and they become more and more experts in what they're doing. So what the generator does is it takes random noise, it generates fake images from that. The discriminator actually tries to tell whether this is data that's coming from the real training set or a fake image, and learns how to discriminate between the two. And this works really, really well. And this, for example, is an example of how well that actually works in these days. So these are images of people that do not exist. Okay, so this is a paper from people at NVIDIA who obviously have a lot of computing power. And in computing power, it's an insane amount of resources that went into it. If I'm not mistaken, something around 50 years of raw computing power on the best machines. Go and read that paper. It's really cool. And the results are quite amazing, right? You can, these really look like photos from real images, from real people. And you cannot distinguish with a human eye whether this is actually a fake picture or a real picture. Now, something that's coming about in these GANs in these days, because everybody is so fascinated by how powerful they are, is that they tend to overrepresent the majority category here. So if you have a training set that has majority white people that go in, well, in the result, it will even bias this result towards more white people. If you want to take this in a less political realm of people's color of the face, car companies use this algorithm, or try to use that algorithm, to generate fake training data so that they can train self-driving cars using the fake training data. In these days, cars often are black or silver or white, but not colorful, right? And if you have then a second deep net or a second algorithm that tries to learn from this fake data about how to self-drive cars, if this algorithm sees less colored cars than there are in reality, this might lead to problems, right? So this is something that people are currently working on, how to wrap your head around the fact that the results here might be biased. Okay, so this is really a quick outlook. The field of deep learning is progressing at an insane pace. It's really exciting. There's a lot going on. For this class, I took the classic book from Ian Goodfellow, the guy who invented GANs, and he wrote this book. I think it's a couple of 600, 700 pages. It's massive. It's really good. You can download it for free on the internet. Go and check out that book. It's really in depth. The first step that I find quite useful when teaching is this book. I drew on other internet resources, the deep learning specialization from Andrew Ng on Coursera. This is a great deep learning papers reading roadmap that's still fairly up to date. These are the MLR3 people. And if you want to learn more about hyperparameter tuning, I think then they are doing a very good job in explaining how that all works together. Okay, this is it from myself. I really, even though I'm only speaking to a screen, I'm really enjoying the questions, and left 5 minutes to see whether there are any other questions left. In case you are working with or on deep learning in this, like in general or in particular in the social science context, always feel free to get in touch with Marcel and myself. Okay, you can find our email addresses here. We have both Twitter handles. Please get in touch. We really are happy to follow up with whatever you are working on, whatever you are doing. Okay, let's see. Any questions? There are 2, 3 questions. Okay. Marcel, I don't think any more questions, right? This is all just praise for you and myself. This is really cool. Whew.
Yeah, no questions.
Yeah.
Yeah, I don't think anything there is on YouTube, nothing there, only lots of gratitude, thank yous, and thanks so much for such a great session. Yeah. Okay, thank you, Chris and Marcel, for doing it today. It was great, lots of gratitude, both in the chat and YouTube. Yeah, thanks everyone.
No, thank you. This was really cool. And I'm looking forward to times when we can do that in person again. This isn't bad, but teaching in a room makes you feel much more like a rock star than teaching to the screen, I think. Yeah, I'm really looking forward to running in any of you. And as mentioned, seriously, in case you have any questions, feel free to get in touch. The material is all online. Yeah, looking forward to any kind of chat we might have in the future.